Hello there, and welcome to Space Sleep Journey, where curiosity takes the gentle shape of a bedtime story and science moves at the pace of a quiet breath. I am so glad you are here tonight. Wherever you are, whatever kind of day is finally letting go of you, you have found your way to a quiet place, and there is nothing you need to do here but rest. Tonight we will be wandering slowly toward one of the strangest questions in all of space, a question that has waited unanswered inside the equations of physics for more than 50 years. What is a quark star really? Could there be a star out there in the dark that is heavier and denser even than a neutron star? A whole star holding more than the weight of the sun in the space of a small town, and yet is somehow not a black hole? A star made of matter crushed so far that it has forgotten how to be atoms at all. We are going to turn that question over gently all night long, the way you might turn a smooth stone in your hand, looking at it from every side, in no hurry at all to reach the end. Before we begin, I always like to wonder where you are listening from tonight. Perhaps you are in a bright and busy city, where the glow of the streets washes almost all the stars from the sky, and only the boldest few shine through, and the night is never quite dark. Or perhaps you are somewhere quiet and far from the lights, out where the countryside lies still, and the whole spilled river of the Milky Way pours softly overhead, and the dark is deep and full of stars. Wherever you are, whether the sky above you is crowded with light or scattered with 1,000 quiet stars, you and I are looking up at the very same universe tonight, and that same universe holds the strange and distant thing we are about to wonder about together. If you find as the night goes on that this quiet voice helps you soften and drift, I would be grateful if you tapped the like button or subscribed, so that others who need a calm voice in the dark can find their way here too. It is a small thing, and it helps this quiet corner of the world reach the people who are looking for it. And now, take a slow breath in and gently out. Settle into your chair or sink down into your pillow and let your body grow just a little heavier where it rests. There is nowhere you need to be and nothing you need to solve before morning. The day begin to loosen its hold on you. We are only going to wander slowly in the dark and let the wandering carry us both towards sleep. Imagine the night is clear and cool, and the stars have come out one by one until the whole sky is dusted with. You are lying back, looking up, and somewhere in all that darkness there is a thing we have never seen. Gives off almost no light of its own. It has no fire burning inside it. It has no hard shell you could ever touch. And yet it may be heavier than the sun, folded down into a ball only 12 miles across, a single spoonful of it heavier than a mountain, made of matter so strange that the smallest pieces of the world have been crushed out of their prisons and set loose to roam. Maybe sitting out there right now, quiet as a held breath, turning slowly in the dark, wearing the face of something more ordinary, keeping its secret. And tonight, gently and without any hurry, we are going to wonder what it truly is. So let us begin where every good question begins, which is with something you already know. You know that the ground beneath you feels solid. You can press your hand against a table and it pushes back. You can hold a stone and feel its weight settle into your palm. All of that feeling, all of that solidness is a kind of gentle lie that matter tells you. Because if you could look closely enough, closer than any eye can ever look, you would find that the stone in your hand is almost entirely empty space. The tiny cores of its atoms, the little bundles we call nuclei, are so small and so far apart that if one of them were the size of a marble set down in the middle of a great cathedral, the next marble would be resting somewhere out past the far wall. Everything solid you have ever touched is mostly nothing at all, held into shape by quiet forces you cannot see. And that is where our question tonight is hiding. Because if matter is mostly empty, then a strange thought follows softly behind it. What would happen if you could push all that emptiness out? What would happen if you took a thing and squeezed it until there was no room left for the emptiness to hide in? How heavy would it become? How small? And is there a limit, somewhere out there in the dark, to how far nature will let you go before something breaks, before matter itself gives up the shape it has always worn and becomes something we have never seen? Tonight we are wandering toward the edge of that question, toward an object that may or may not exist, an object called a quark star. I want you to hold that name lightly for now. Quark star. We will come to what it means slowly, the way you would come to the edge of a lake in the dark, feeling your way, letting your eyes adjust. There is no hurry here. We have the whole night and the whole sky, and the question is patient. It has been waiting inside the equations of physics for more than 50 years, quietly, without answer. So we can afford to be patient too. Let me start by drawing you a kind of staircase. Picture a staircase that leads downward into greater and greater density, into matter squeezed tighter and tighter. On the top step, where things are gentle and familiar, sits ordinary matter, the matter of your body and your bed and the tree outside your window. Take a step down and you reach the matter inside a very old star that has died and shrunk, a thing called a white dwarf. Take another step down and you reach a neutron star, denser still, one of the strangest things the universe is known to make. And then there is one more step, a step we are not sure exists, a step that may be real or may be only a beautiful idea. That step is the quark star. And below even that, at the very bottom of the staircase, waits the black hole, where matter falls away entirely and nothing we know can describe what happens next. So our whole journey tonight is really a journey down this staircase, one careful step at a time, until we reach that uncertain step near the bottom and stand there together, looking at it, asking whether it holds any weight at all. Could a star exist that is heavier and denser than a neutron star, and yet is not a black hole? That is the heart of it. That is the single question we will follow into the dark. To understand the strange step, we first have to understand the steps above it, the ones we are more sure of. So let us begin at the top and walk down slowly and I promise that by the time we reach the bottom, the strangeness will feel less like a shock and more like the natural end of a path we walked together. Think first about an ordinary star, a star like our own sun. A star is a long, slow argument between two forces that never fully agree. On one side there is gravity, always pulling inward, always trying to crush the star down into a smaller and smaller ball. On the other side there is pressure, pushing outward. In a living star like the Sun, that outward pressure comes from heat, from the nuclear fire burning in the core, where hydrogen is squeezed into helium and light is born. That fire pushes out. Gravity pulls in. And for billions of years the two of them lean against each other, almost evenly matched, and the star holds its shape and shines. But a fire needs fuel, and no fuel lasts forever. One day, far in the future, the sun will run low on the hydrogen it burns. The fire in its core will falter. And when the fire falters, the outward push weakens, and gravity, which never tires and never rests, begins to win. Core starts to fall inward on itself. This is the moment every star must eventually face, the moment when the long argument tips at last toward gravity. For a star about the size of our Sun, the falling does not go very far. As the core shrinks, something quiet and deeply strange steps in to stop it. To understand what stops it, we have to leave the world of ordinary things for a moment and go down among the very small, down to the particles that everything is made of. Stay with me here, gently, because this small idea is the key to the whole night. Everything around you is built from atoms, and an atom, as I said, is mostly empty. At its center is the nucleus, and around the nucleus in a soft cloud are the electrons. Now electrons have a rule they must obey, a rule that nature never bends. No two electrons are allowed to sit in exactly the same state, in exactly the same place at the same time. Each one must have its own little room, its own place to be. This rule has a long name, but you do not need the name. You only need the picture. Picture a great house with rooms, and a rule that says only one guest may sleep in each room. When the house is nearly empty, this rule means nothing. There is plenty of space. But as more and more guests arrive, the rooms fill up, and the guests are forced into rooms higher and higher in the house, further and further from the ground, because the lower rooms are already taken. Crowding creates a kind of pressure, and here is the wonderful part. It is a pressure that has nothing to do with heat. Even if you cooled the house to the coldest cold there is, the guests still could not share rooms, and so they would still push against each other, still refuse to be squeezed closer. Physicists call this degeneracy pressure. It is the stubbornness of matter, the refusal of the smallest things to be crowded past a certain point. And it is this stubbornness, the stubbornness of electrons, that catches the collapsing core of a dying sun and holds it up. When electron stubbornness stops the fall, what is left behind is a white dwarf. take a good look at it, because it is our first step down the staircase. A white dwarf is the burned core of a star, and it is astonishing on its own. You take something roughly as heavy as the sun, and you pack it down into a ball about the size of the Earth. Think about that for a moment. The sun is so large that if it were hollow, you could pour more than 1,000,000 Earths inside it. And a white dwarf takes nearly all of that mass and folds it down until it is no bigger than our small planet. A single spoonful of white dwarf matter would weigh about as much as a large truck. That is the first step down into density, and already it strains the imagination. But the sun is a gentle star, and a white dwarf is a gentle ending. The staircase goes deeper for stars that are born much larger. So let us turn now to those larger stars, the heavy ones, because it is only in their deaths that the next step becomes possible. A star much heavier than the sun lives a faster, fiercer life, burns through its hydrogen quickly, then burns the helium that hydrogen leaves behind, then burns heavier and heavier fuels in a series of shells like the rings inside a tree, each ring hotter and denser than the one outside it. Burns carbon and oxygen and on, climbing up the ladder of the elements, forging heavier atoms in its core with each stage. And every element it makes by fusing lighter ones together, and every fusion gives off a little energy, a little outward push to hold gravity back for a while longer. This climb cannot go on forever either, and the reason it cannot is one of the quiet turning points of the whole universe. The star keeps fusing heavier elements until it reaches iron. And iron is special. Iron is the ash at the end of the fire. When you try to fuse iron, you do not get energy back. You have to spend energy instead. Iron sits at the very bottom of a kind of valley, the most tightly bound, most contented nucleus there is. Nothing you do to it will give you an easy return. Remember that fact about iron and hold on to it, because it is going to come back to us later tonight in a way you will not expect when we ask what the most stable form of matter in the universe truly is. So the great star builds a core of iron, and the iron core cannot burn, and so the fire that held up the star finally truly dies. And now gravity, which has been waiting all this time, collapses the core in less than a single second. The fall is almost unimaginably violent. The core, which was already denser than anything on Earth, is crushed inward at a fair fraction of the speed of light. And this time, the stubbornness of electrons is not enough to stop it. Gravity is simply too strong. The electrons are driven down into the atomic nuclei themselves, forced to merge with the protons they find there, and in that merging something new is made. The protons and electrons become neutrons. The whole core, in a heartbeat, turns into a vast sea of neutrons packed shoulder to shoulder. And now a new stubbornness takes over, because neutrons obey the same rule that electrons do. They too refuse to share a room. So when the core has become a solid crush of neutrons, Their degeneracy pressure slams on like a wall, and the collapse is halted suddenly and with tremendous force. The outer layers of the star, which were racing inward behind the core, come crashing down onto that wall and rebound off it in a shock that tears the whole star apart. This is a core collapse supernova, one of the brightest events in all the sky, a single dying star that for a few weeks can outshine the entire galaxy of hundreds of billions of stars around it. And when the light finally fades and the wreckage drifts away into space, there, at the center of it all, sits the thing left behind. A neutron star. Our second step down the staircase, and the doorway to everything strange that follows. I want us to stay with the neutron star for a good long while, because you cannot understand a quark star until you understand how far a neutron star has already gone, and how it is already, by any honest measure, one of the most extreme objects nature knows how to build. So take a slow breath and let us walk out onto that second step together and look at what is standing there in the dark. A neutron star is a small thing, and that is the first surprise. When we speak of stars, we are used to speaking of things so large that our whole world would vanish inside them like a grain of sand. The sun is nearly 1,000,000 miles across. But a neutron star is not like that at all. A neutron star is only about 12 miles across. 12 miles. If you set one down on the Earth, it would not even cover a single city. You could drive from one side of it to the other in the time it takes to eat a quiet meal. It is the size of a town, and yet it is a star, and it holds inside that little body more mass than the sun. Let me say that again slowly, because it is the kind of thing the mind slides off of the first time it hears it. Take the sun, that enormous furnace that holds all the planets in their paths, that could swallow more than 1,000,000 Earths. Take about 1.5 times all of that mass. And now pack it, without losing any of it, into a ball the size of a town, only about 12 miles from edge to edge. That is a neutron star. All the weight of a great star, folded down into something you could walk across in an afternoon, if walking across it did not destroy you utterly. And it would destroy you in ways that are almost hard to speak of gently. Pull of gravity at the surface of a neutron star is so strong that it beggars every comparison we have. To lift yourself even the smallest height against that pull would take more strength than any engine we have ever built. If you dropped a single small stone from just above the surface, it would strike the ground moving at a fair fraction of the speed of light. The star does not merely hold you down, it flattens the very idea of standing. Nothing with a shape as loose and soft as a living body could keep that shape for even an instant there. But it is the density that we came to speak of, because density is the thread that runs through this whole night. So let me try to give you the density of a neutron star in a way you can feel. And I am going to return to this image more than once tonight, because it is worth returning to. It is one of those facts that does not wear out. Imagine a single teaspoon. An ordinary teaspoon, the kind you would stir into a warm drink before bed. Now imagine filling that teaspoon, just that small hollow, with the matter from inside a neutron star. How much would it weigh? It would weigh about 1 billion tons. One small spoonful. About 1 billion tons. That is more than the weight of every car in a great nation piled together. That is a mountain folded down into the bowl of a spoon. If you could somehow hold that spoonful here on Earth, it would tear straight through the spoon and through the floor and through the ground, and it would fall, gathering speed, all the way toward the center of the Earth, because nothing we have could hold it up. Sit with that for a moment. Teaspoon that weighs as much as a mountain. That is not a trick of words. That is a real measurement of a real kind of matter. Matter that exists right now, tonight, in perhaps 100 million such stars scattered through our galaxy alone. The universe is full of these tiny, impossible weights, spinning quietly in the dark, and most of them we will never see. Now here is a question you might already be asking, softly, in the back of your mind. If a neutron star is a ball of neutrons packed shoulder to shoulder, why does it stop there? Why does it hold that particular size, that particular density, and not shrink further? And the answer, as we have already touched, is the stubbornness of the neutrons, their refusal to share a room. That refusal creates the neutron degeneracy pressure, and it is that pressure, and not any fire, that holds the star up. There is no burning inside a neutron star. It shines faintly only because it is still warm from the terrible heat of its birth, cooling slowly across the ages like an ember pulled from a fire and left in the dark. It is held up not by heat, but by a rule of the very small, the same rule that once held up the white dwarf, only now pushed to a far greater extreme. And this is the exact place where our question is born, so let us stand here carefully and look closely. Because if a white dwarf can be crushed past the stubbornness of its electrons, when gravity grows strong enough, then a fair and honest mind must ask the next question. Can a neutron star be crushed past the stubbornness of its neutrons? Is there a weight, some particular heaviness, at which even the neutrons can no longer hold the line? The answer, as far as we can tell, is yes. There is such a weight. Add enough mass to a neutron star, pile enough on, and the neutrons at its heart will begin to lose their fight. And here is where the path splits, and where the whole mystery of the night opens up before us. When the neutrons finally begin to give way, what happens next? What comes after the neutron? One possibility is the simplest and the most final. The matter simply keeps falling. There is nothing left to stop it, no deeper stubbornness to catch it, and so it collapses all the way down, past every limit, until it disappears behind that one-way door we spoke of, the event horizon, and becomes a black hole. Down the last step of the staircase, into the dark that swallows even light. But there may be another possibility. And this other possibility is the quark star. It is the idea that there is one more step, one more landing on the staircase between the neutron star and the black hole. Place where matter, crushed past the point where neutrons can survive, does not fall all the way into a black hole, but instead settles into a new and even denser form, a form we have never seen and are not certain exists. To understand what that new form might be, we have to go inside the neutron itself, down below the neutron, to the smaller things that a neutron is made of. And that is where the word quark finally comes in. So let us go there together, gently and slowly. Let us open up the neutron and look at what is inside. For most of human history, we thought the smallest pieces of the world were the atoms themselves. The very word atom comes from an old word that means uncuttable, the thing you cannot divide any further. But we learned over the last century or so that the atom can be cut after all. Inside it is the nucleus, and around it the electrons. And then we learned that the nucleus itself can be cut, that it is made of smaller pieces still, the protons and the neutron. And for a while we thought perhaps those were the end of the line, the truly uncuttable things. But they were not the end either. In the years that followed, we discovered that the proton and the neutron are not simple little balls at all. Each one is itself made of smaller pieces, 3 smaller pieces, and those pieces we call quark. A neutron, that tiny thing of which a whole star can be made, is itself built of 3 quarks, bound together so tightly that under all ordinary conditions you can never pull them apart. A proton is 3 quarks as well, a slightly different set. Quarks are, as far as we know today, truly among the smallest things there are. We have never found anything inside a quark. They may be the bottom of the ladder, the true uncuttable things that the old thinkers were dreaming of all along. Now the quarks inside a neutron come in kinds, and the kinds have names that are only names, chosen playfully by the people who found them. There is a kind called up, and a kind called down. Do not read anything into those words. They do not point up or down in space. They are just labels, the way we might call 2 children by 2 names to tell them apart. A neutron is made of 1 up quark and 2 down quarks. A proton is made of 2 up quarks and 1 down quark. There are heavier kinds of quark as well, with names like strange and charm and top and bottom, and one of those, the strange quark, is going to matter a great deal to us before the night is over. But for now, hold just the 2. And down. 2 quarks that build the ordinary matter of the world. Here is the thing about quarks that makes them so unlike anything in daily life, and it is the very thing our whole question turns upon. Quarks are never found alone. You cannot take a neutron and pull out a single quark and hold it up to the light and study it by itself. It has never been done, and as far as we understand the laws of nature, it cannot be done, at least not in any ordinary way. The quarks are locked together, imprisoned inside the neutron, and the force that imprisons them is the strongest force in all of nature. It even has that name. We call it the strong force. And to understand a quark star, we have to understand something about this force and about the strange way it behaves, because a quark star, if it exists, is nothing less than a place where the strong force has been beaten, where the prison has been broken open, and the quarks have been set loose to roam. So let us turn now to the strong force, and to the prison it builds around every quark, and let us see, gently and without any hurry, how such a prison might ever be broken. Take a breath. We are going deeper now, but the path is still smooth beneath our feet, and I am still here beside you, and there is nothing to fear in any of it. It is only the universe showing us how deep its strangeness goes. The strong force is the strangest of all the forces, and it behaves in a way that runs exactly opposite to your every instinct. So let me build the picture slowly, because if you can feel this one strange thing, then the rest of the night will open like a door. Think about the forces you already know. Think about gravity. When you are close to the Earth, its pull is strong. As you move away out into space, the pull grows weaker and weaker. The farther apart two things are, the more gently gravity draws them. Think about a magnet. Hold it near a nail, and the nail leaps to it. Pull it away, and the grip fades quickly. This is how almost every force we know behaves. Close means strong. Far means weak. It is so familiar that we never even think to question it. The strong force does the opposite. When two quarks are very close together, almost on top of each other, the strong force between them is gentle, so gentle that the quarks can drift about almost freely, as though they were hardly bound at all. But as you try to pull two quarks apart, the force does not fade. It grows. The farther you pull them, the harder it pulls back, like a spring or like a band of elastic that only tightens the more you stretch it. Try to separate two quarks, and the force between them climbs and climbs, refusing to let go, growing stronger the more distance you put between them. This has a beautiful consequence, and a strange one. It means you can never pull a single quark free. If you grab a quark and try to drag it out of a neutron, the strong force pulls back harder and harder as you go, storing up more and more energy in the stretched bond between them, until at last so much energy has piled into that bond that the energy itself turns into new quarks. A fresh pair of quarks simply appears out of the stored energy, one of them rushing to join the quark you were pulling, the other staying behind. And so instead of a lone quark in your hand, you are left with two little bundles again, each one whole, each one still a prison with its quarks locked inside. Pull as hard as you like. You never get a free quark. You only ever make more prisons. This is what physicists mean when they speak of confinement. Quarks are confined, sealed away, never to be seen alone under ordinary conditions. The name for the deep theory that describes all of this is a long one, and you do not need to carry it, but I will set it down once so it is not a stranger if you meet it. It is called quantum chromodynamics, which only means the study of the color force, and the color has nothing to do with the colors your eyes can see. It is just a name that physicists borrowed, a label for the kind of charge that quarks carry, the way an electron carries electric charge. There are 3 of these color charges, and they are only called red and green and blue as a bookkeeping trick, a way to keep the accounts straight. The rule of the strong force is that quarks may only gather in groups whose colors cancel out to something colorless, something balanced, the way red and green and blue light together make white. A neutron is such a balanced group. A proton is such a balanced group. Always balanced. Always colorless. Never a lone color wandering free. Now here is where the door begins to open. Because there is one more feature of the strong force, and it is the feature on which the whole idea of a quark star hangs. Remember that the force is gentle when quarks are close, and fierce when they are far apart. What that means is this. If you could somehow force a great many quarks very close together, closer and closer, into a smaller and smaller space, then the force between any 2 of them, being gentle at close range, would relax. Prison walls, which are built out of distance, would begin to lose their meaning. When everything is crammed together so tightly that no quark has any room to be far from another, then no quark can be pulled far from another, and the fierce restoring pull never has a chance to build. In such a place, the quarks would no longer belong to any one neutron. They would no longer each have their own little prison. They would be free to wander through the whole crush of matter, sliding past one another in a single vast sea. Physicists have a word for this too. They call it deconfinement. The quarks are deconfined, released from their separate cells, not because the prison was broken from outside, but because everything was pushed so close together that the walls between the cells simply melted away. Do you feel the shape of the idea now? Do you see where the night has been carrying us? A neutron star is a ball of neutrons, each neutron a little prison holding its 3 quarks. But if you press on that ball hard enough, if you pile on enough mass so that gravity crushes the core to a density even beyond the density of the neutrons themselves, then down in that deepest heart, the neutrons may be squeezed so close that they lose their separateness. The walls between them melt. Quarks pour out of their cells and mingle into one great sea of free-roaming quark matter, deconfined, unbound from any single neutron. And a star with a heart like that, or a star made entirely of such matter, would be a thing beyond the neutron star. Would be a quark star. That is the idea, laid bare. That is the whole seed of it. But an idea is not a thing. And I want to be honest with you all through this night about the difference between what we know and what we only suppose. So let me say it plainly here, and I will say it again more than once, because the honesty is part of the peace of it. No one has ever proven that a quark star exists. No one has ever held one in the crosshairs of a telescope and said, with certainty there, that one That is a star made of free quarks. The quark star lives, for now, in the borderland between what our equations allow and what our instruments have confirmed. It is permitted by the laws as we understand them. May well be out there, but it is not being caught. Hold that lightly, the way you would hold a candle in a large dark room, grateful for the light it gives, not pretending it lights the whole room. Now, if the idea stopped there, it would already be strange and lovely enough to carry us through the night. A star whose heart has dissolved into free quarks. The idea has a deeper, wilder cousin, and I would be keeping something from you if I did not bring it out into the open, because it is one of the most surprising thoughts in all of physics, and it turns the whole question upside down. To reach it, we have to go back to iron. Do you remember the iron? Earlier tonight I asked you to hold on to a small fact and carry it forward. The fact that iron is the ash at the end of a star's fire, the most tightly bound and contented nucleus there is, the bottom of a valley from which nothing gives an easy return. We have always thought of iron as the most stable form of ordinary matter. Left alone forever, with all the time in the world, ordinary matter would like to become iron and rest there. That has long been part of how we understand the world. But in the early 1970s, and then again more famously in the middle of the 1980s, a small number of physicists asked a question that sounds almost mischievous. What if iron is not truly the bottom of the valley? What if iron only seems like the bottom because it is the lowest place that ordinary matter made of up and down quarks can easily reach? What if there is a deeper valley somewhere nearby, a lower and more restful place, that ordinary matter simply cannot get to by any easy road because the road there is blocked? The deeper valley they imagined has a name. It is called strange matter. And to understand it, we have to bring back that third kind of quark I mentioned earlier, and then set aside. The strange quark. Let us pick it up again now, because it is about to become the center of everything. Ordinary matter, as we have said, is built from just two kinds of quark, the up and the down. Every proton, every neutron, every atom in your body and in the whole familiar world is made from those two, and only those two, arranged and rearranged. The other kinds of quark are heavier, and heavier things in the world of the very small tend to be fleeting. They flicker into being in great collisions and then decay away almost at once, turning back into the lighter kinds. The strange quark is one of these heavier, fleeting ones. It is more massive than the up or the down, and in ordinary matter it simply does not last. So we do not find it lying around. The world we know is an up and down world. But now imagine a place where matter has been crushed to an unthinkable density, the density we might find in the crushed heart of a heavy dead star. In such a place, the quarks are packed so tightly and pressed to such high energies that a curious door opens. Remember the rule of the rooms, the rule that no two identical particles may share a state. When you have an enormous crowd of only up and down quarks, packed as tight as they will go, the rooms for up quarks are all full, and the rooms for down quarks are all full, and to add even one more you must place it in a very high and costly room, far up the house. The strange quark is a different kind. It has its own separate set of rooms, all of them empty, waiting lower down. And so, past a certain density, it can actually cost the matter less energy to turn some of its down quarks into strange quarks and let them settle into those lower empty rooms than to keep piling up quarks into the crowded higher rooms of the kinds it already has. When that happens, the matter is no longer made of two kinds of quark, but of three. Up, down, and strange, all together in roughly equal measure, sharing the crush. And this three-kind matter has a lower energy than the two-kind matter did. It has found a way down into a deeper, more restful valley. This is strange matter. Matter that has discovered that adding a third flavor of quark lets it settle lower than ordinary matter ever could. And here is the thought that turns everything over, the thought that a physicist named Arnold Bodmer first set down in the early 1970s, and that another physicist, Bodmer-Witten, developed and made famous in the middle of the 1980s. What if this strange matter is not just a deeper valley reachable only under crushing pressure? What if it is the deepest valley of all? What if strange matter once made is more stable than iron itself? More stable than anything? What if strange matter, and not iron, is the true and final resting place of matter, the real bottom of the whole landscape, the thing that everything would become if only it could find the road? This is what people call the strange matter hypothesis, and it is often named for those two men, the Bodmer and Witten idea. And notice, please, that word. Hypothesis. It is a supposition, an if, a beautiful maybe. It has never been proven, and it may well be wrong. But let us follow it a little way, because it leads somewhere breathtaking. If strange matter really is more stable than iron, then a strange and quiet question follows. Why is the world around us not already made of it? Why are you and I and the earth and the sun made of ordinary up and down matter, if there is a deeper, more restful form waiting below us? And the answer is the same reason a ball can rest on a shelf even when the floor is far below. To get from the shelf to the floor, the ball would first have to be lifted over the edge. There is a barrier in the way. Ordinary matter sits on a shelf. Below it, perhaps, is the deeper floor of strange matter. But to get there, ordinary matter would have to change many of its quarks into strange ones all at once, and that is so unlikely, so nearly impossible, that it essentially never happens on its own. We are stable not because we are at the bottom, but because the road to the bottom is blocked by a wall too high to climb. We are safe on our shelf. And that, when you think about it, is a rather comforting thought to hold in the dark. Down in the heart of a dying star, where matter is crushed past all ordinary limits, the wall can be climbed. The pressure itself can push matter over the edge of the shelf and down into the deeper valley. And once it lands there, once a patch of true strange matter has formed, it might be stable forever, resting in that deepest valley, needing no gravity and no fire to hold it together, bound by the strong force alone into a single quiet. And a whole star made of that stuff has its own name. We call it a strange star. So now we have two closely related ideas, and I want to hold them side by side for you gently so that you can see how they differ, because people often blur them together, and the difference is worth a moment of care. The first idea is the quark star in its planar form. Picture a neutron star that has been made heavy enough that only in its deepest core, in the very center, do the neutrons dissolve into free quark, while the outer layers remain ordinary neutron matter. Such a star is a neutron star with a small, strange heart, a quark core wrapped in a neutron shell. Physicists often call this kind a hybrid star, because it is a hybrid, a blend, part neutron matter and part quark matter, layered like the inside of a fruit with a different center than its skin. The second idea is the pure strange star, and it is the wilder one. If the strange matter hypothesis is true, if strange matter really is the most stable form of all, then a star need not be part neutron and part quark. It could be strange matter almost all the way through, from its deep center nearly to its very surface, a single vast lump of up and down and strange quarks bound together by the strong force into one continuous body. Such a star would not be held up mainly by gravity fighting pressure, the way ordinary stars and neutron stars are. It would be self-bound, held together by the strong force itself, the way a drop of water is held together by the pull of its own surface, needing no container. In fact, a strange star could, in principle, exist even with very little mass at all, held together not by its weight, but by the strong bond of the strange matter itself, right down to a sharp and sudden surface where the matter simply stops. Take a moment with that picture, because it is one of the strangest in the whole night. A star with a true surface. Not a soft fading edge of thinning gas like the sun, and not the faint thin crust of a neutron star, but a sharp and sudden wall where the strange matter ends as cleanly as the surface of a stone, a boundary, only a hair's breadth thick, below which lies matter, 1,000,000,000,000 times denser than water, and above which lies nothing but empty space. A bare surface of pure quark matter, gleaming in the dark. If such a thing exists, it is like nothing else the universe is known to make. So when we say quark star tonight, let us mean the whole family of these ideas, all the ways that matter might live in that uncertain landing between the neutron star and the black hole. The hybrid, with its quark heart and neutron skin. Pure strange star, self-bound and sharp-edged, and every shade of possibility in between. They are cousins, all of them children of the same question, the question of what comes after the neutron, when the neutron can hold no more. And now that we have the idea in its full strangeness, we come to the questions that a careful mind cannot help but ask next. How heavy would such a star be? How small? Denser even than a neutron star, or lighter? And most of all, How, in the name of everything, could we ever hope to know if one truly exists when we cannot even pull a single quark free to look at it here on Earth? Let us take those questions one at a time, slowly, beginning with the simplest of them, the size and the weight, and let us see just how far past the edge of the ordinary these objects would sit. Let us talk first about weight, and let us do it gently, because the numbers here are large, and it is easy to let large numbers wash over you without feeling them. I do not want them to wash over you. I want each one to land softly and stay. A quark star, if it exists, would weigh somewhere between about 1.5 and about 2 times the mass of our Sun. That is the window the physics seems to allow. Below that range, an ordinary neutron star does the job, and there is no need to invoke anything stranger. Above that range, something else takes over, and we will come to what that something is very soon. So the quark star, if it is real, lives in a narrow band of weight, roughly 1.5 to 2 suns, right in the crowded neighborhood where the heaviest neutron stars also live. That closeness is part of what makes the mystery so hard, and we will feel the weight of that difficulty before the night is done. Now the size. A neutron star, we said, is about 12 miles across. A quark star would be smaller still. The best estimates put its radius at something like 6 or 7 miles, which means it might be only about 12 to 14 miles from one side to the other, perhaps even a touch less. So picture it. The mass of 1.5 or 2 suns, more mass than a neutron star holds, and pack it into a ball even smaller than a neutron star. A ball you could walk across in a single afternoon if it did not annihilate you first. More weight, less room. That is the whole meaning of the word denser. A quark star would be the densest form of matter that can still hold itself together and remain a star, the densest thing in all creation short of a black hole, where matter stops being a thing at all. Let me try to give you that density in a way you can hold, the way I gave you the neutron star's teaspoon. We said 1 teaspoon of neutron star matter weighs about 1 billion tons. Teaspoon of quark star matter would weigh even more, for it is denser still, matter squeezed past the neutrons into a smaller space. Try to picture it if you can, though I confess it lies almost beyond picturing. A single small spoonful, heavier than a mountain range. Heavier than a range of mountains stretching past the horizon. And a whole star of it, all folded into the space of a quiet town, sitting somewhere out in the dark, turning slowly, giving off almost no light, wearing a face so like a neutron star's that even now, tonight, with all our instruments, we cannot always tell the two of them apart. There may be one out there that we have already seen, already catalogued, already given a plain name to, without ever knowing what it truly was. And there is that other feature, the strangest one, that sets the pure strange star apart from every ordinary star. It would be self-bound. Let me linger on that word, because it changes the whole character of the object. Every ordinary star, and every neutron star too, is a balance, a truce between gravity pulling in and pressure pushing out. Take gravity away, and the star would fly apart. It exists only because its own great weight is holding it together against the pressure that would scatter it. But a strange star, if the strange matter idea is right, would not need its weight to hold it. The strong force would bind it directly, quark to quark, the way the strong force binds the inside of a single neutron. It would hold together for the same reason a stone holds together, or a drop of water keeps its shape from the inside by its own cohesion, not from the crushing weight of everything above. That difference has a consequence so strange it is almost playful. An ordinary neutron star cannot be small. If you tried to make one with very little mass, its gravity would be too weak to squeeze it to neutron density, and it would simply spring back into something ordinary. Neutron stars must be heavy to exist at all. But a strange star, held together by the strong force rather than by gravity, could in principle be any size, even quite small, held together just as firmly, whether it were as heavy as a sun or, in the wildest imaginings, no heavier than a mountain. There might, in theory, be small lumps of strange matter, called strange nuggets, drifting through space, tiny and dark and unthinkably dense, each one a chip off some ancient event, wandering between the stars. No one has ever found one. The mathematics does not forbid them, and that is a haunting thing to carry with you on a dark night. The thought that the space between the stars might not be as empty as it looks. So we have our object now drawn as fully as the physics allows, between 1.5 and 2 suns in weight, only 12 or 14 miles across, denser than a neutron star, a spoonful heavier than a mountain range, possibly self-bound, possibly sharp-edged, possibly the true and final resting place of all matter, and unproven. Always gently unproven. Now let us turn to the question that guards the whole idea like a locked gate, the question of the limit. How much can a star weigh before it can no longer be any kind of star at all, before it must fall the last step into a black hole? Because the quark star, if it lives anywhere, lives right up against that limit in a narrow window just below the final door. There is a number for this limit, or rather a range, because we do not know it exactly, and the not knowing is itself a large part of tonight's story. The limit has a name made of 3 names, the names of 3 of the people who first worked it out. It is called the Tolman-Oppenheimer-Volkoff limit, and people who speak of it often shorten it to just its initials to save their breath. It is the greatest mass that a cold, still, compact star can hold before its own gravity overwhelms every possible source of pressure and crushes it without appeal into a black hole. It is the last fence at the edge of the cliff. Cross it, and there is no more standing. There is only the fall. The story of this number is itself a small and human one, and worth telling gently. Back in the year 1939, 2 physicists, Robert Oppenheimer and George Volkoff, building on earlier work by Richard Tolman, sat down to ask how heavy a neutron star could be. Neutron stars had not yet been seen. They were themselves only an idea then, a fresh and daring one. And when Oppenheimer and Volkoff did their calculation, leaving out some of the complicated ways that neutrons push on one another, forces that were not yet understood, they found a limit of only about 7/10 of the mass of the Sun. A small number. Almost a discouraging one. It suggested that neutron stars, if they existed at all, could barely outweigh the Sun. That early number was too low because it left out how stubbornly neutrons resist being packed together, forces we came to understand only in the decades that followed. As those forces were added in, the limit climbed. By the latter part of the 20th century, careful work had raised it to somewhere between about 1.5 and 3 times the mass of the Sun, a wide and uncertain range. And today, with everything we have learned since, the best estimates place the limit for a still, non-spinning star at somewhere around 2 1/10 to about 2 3/10 times the mass of the Sun, though even now the exact figure remains just out of our grasp, because it depends on something we still do not fully know. And that something has a name, and it is perhaps the single most important unknown in this whole night. It is called the equation of state. Let us turn to it now, because it is the true heart of the mystery, the reason the quark star hides from us so well, and the reason that answering our question is so very hard. The equation of state is a grand-sounding name for a simple and homely idea. It is nothing more than the answer to a single question asked of any kind of matter. When you squeeze it, how hard does it push back? That is all. If you press on a thing, how much does it resist? A soft thing, a pillow, gives way easily and pushes back gently. A hard thing, a block of steel, barely yields at all and pushes back with tremendous force. The equation of state is just the rule that tells you, for a given kind of matter, how much pushing back you get for a given amount of squeezing. Soft matter and hard matter. Yielding and stubborn. That is the whole idea, dressed in a formal coat. Now, for the matter of everyday life, we know the equation of state very well. We can squeeze water and steel and air in our laboratories and measure exactly how they push back. The matter inside a neutron star and the matter that might make a quark star is packed to a density we can never reach on Earth. We cannot make a teaspoon that weighs 1 billion tons and press on it to see how hard it shoves back. That matter exists only inside these distant dying stars, out of all reach. And so we do not know its equation of state. We do not know with certainty how stubbornly the matter inside a neutron star resists being crushed. And that single gap in our knowledge is the fog that hides the quark star from us. Here is why it matters so much, and I want to walk through this carefully, because once you see it, the whole shape of the mystery becomes clear. Imagine the matter inside these stars is very stubborn, very hard, very stiff. Squeeze it, and it pushes back ferociously. Then that matter can hold up a great deal of weight before it gives, and neutron stars could grow quite heavy, close to 2.5 times the Sun before collapsing. In that case, there is little or no room for a quark star. The neutrons hold the line right up to the black hole, and nothing stranger ever gets a chance to form. Now imagine instead that the matter is softer, more yielding, that it gives way more easily under pressure. Then neutron stars could not grow so heavy before caving in, and there would be a real gap, a real window, in which matter is crushed past the neutrons, but not yet all the way to a black hole. And it is exactly in that window, in that gap left by softer matter, that a quark star could live. So whether quark stars exist at all may come down to this one unknown thing, how stiff or how soft the densest matter is. Learn the equation of state, and you learn whether there is room in the universe for these strange stars. That is why so much patient work is poured into measuring it, and that is what the next long part of our journey is about. So let us ask, as gently and as thoroughly as we can, the question that will fill the deep middle of this night. How do we even know? How could we possibly measure the stiffness of matter we can never touch, inside stars we can barely see, so far away that their light has been travelling toward us since long before there were cities or written words? It seems, at first, like an impossible thing to ask. And yet, over the last 100 years, patient people have found ways, several clever and beautiful ways, to reach out across all that distance and take the measure of these hidden things. Let us walk through those ways, one by one, slowly, because the measuring, truly, is half the wonder. The quark star is a marvel. But so is the fact that we, small and soft and short-lived, standing on one ordinary world, have found ways to weigh a thing 12 miles wide from thousands of light years off. Let me show you how it is done. The first thing we must be able to do, if we are ever to catch a quark star, is to weigh these stars and to measure their size. If we could learn, for even one of them, both how heavy it is and how wide it is, then we could ask whether it is too small for its weight, denser than any neutron star has any right to be, and that would be our first real clue that we were looking at something stranger. So the whole game, in a sense, comes down to two numbers for a single star: its mass and its radius, its weight and its width. Both for the right star, and the door begins to open. Weighing a star that we cannot see clearly, that gives off almost no light, sounds impossible, and yet there is a way, and it is one of the oldest and most trusted tricks in all of astronomy. Most stars do not live alone. They live in pairs, two stars bound together by gravity, circling one another endlessly, like two dancers holding hands and spinning about a shared center. And when two things circle one another, the way they move tells you their weight. A heavy partner and a light partner swing differently than two equal partners do. The heavier a thing is, the more it pulls, and the more it pulls, the faster and the tighter the dance. So if we can watch the dance carefully, and time how long each circle takes, and see how wide the circles are, we can work backward, using the same laws of gravity that hold the planets in their paths, and calculate the mass of each part. This is how we have weighed stars for well over a century. It does not require that we see the star clearly. It only requires that we can watch it move. And some neutron stars make this measurement wonderfully precise through a gift of nature that is almost hard to believe. Many neutron stars spin, and spin very fast, some of them hundreds of times every second, faster than the blades of any machine. And as they spin, they sweep a beam of radio waves around the sky, like a lighthouse sweeping its beam across a dark sea. If that beam happens to sweep across the Earth, then once every turn of the star we receive a tiny pulse, a faint tick, arriving with a regularity so perfect it can rival the finest clocks ever built. We call such a star a pulsar because it pulses. And because the ticking is so steady, we can measure the tiniest changes in its timing. When a pulsar circles a companion, its ticks arrive a little early on one side of the dance and a little late on the other, as the star moves toward us and then away. And from those tiny shifts in timing, we can weigh it with astonishing care. Some of the heaviest neutron stars we know, stars weighing about 2 times the Sun, were weighed in just this way, by listening to the patient ticking of a pulsar and watching how it drifts as the star swings around its partner. Those heavy pulsars matter enormously to our question, and here is why. Every time we find a neutron star that weighs about 2 suns and confirm it, we push up the floor of what the matter must be able to support. A neutron star that heavy proves that the densest matter cannot be too soft, because if it were too soft, it could never hold that much weight without collapsing. So each heavy pulsar we find tells the softer equations of state that they are wrong and rules a few of them out. And in ruling them out, it slowly narrows the window in which a quark star could live. The discovery of neutron stars weighing right around 2 times the mass of the Sun was, for exactly this reason, a quiet turning point. It told us the densest matter is fairly stiff, stiffer than some had guessed, and it tightened the whole puzzle. So we have learned to weigh these stars. That is the first number. The weight alone is not enough. Also need the width, the radius, and measuring the radius of a thing only 12 miles across from thousands of light years away is far harder and far stranger than weighing it. So let us turn to that next, to the delicate and clever ways we have found to measure the size of something we can never truly see. To measure the size of a neutron star, we cannot simply look at it and see a disk, the way you can look at the moon and see a round face. It is far too small and far too far away for that. Seen from Earth, even through our greatest telescopes, a neutron star is nothing but a single point of faint light, no wider than a distant street lamp seen across a valley. There is no disk to measure. So we must be cleverer, and we must let the light itself tell us how big the star is, even when we cannot see its shape at all. Here is the idea, and it rests on something you already know from daily life. A warm thing glows. Poker left in a fire begins to shine, first a dull red, then orange, then a fierce white as it grows hotter. Color of the glow tells you the temperature. and the total amount of light a warm thing gives off depends on two things together, on how hot it is and on how large it is. A small warm ember and a great warm wall might be the same temperature, but the wall pours out far more light simply because it is bigger, because there is more of it glowing. So if you can measure both the temperature of a glowing thing from the color of its light and the total amount of light it sends you, then you can work backward to its size. A hot thing that sends only a little light must be small. A cooler thing that floods you with light must be large. A neutron star, still warm from its violent birth, glows in just this way, though it glows mostly in a kind of light our eyes cannot see, a high and energetic light we call X-rays. We have built telescopes that fly above the air, out in space, to catch those X-rays, because the air of Earth blocks them and would never let them through. And from the X-ray glow of a neutron star, we can read its temperature from the balance of colors within that light, and we can measure the total flood of light it sends us. Two of the three things we need. But there is a catch, and it is a stubborn one, and it has haunted this whole field for decades. To turn the flood of light we receive into the true size of the star, we must know exactly how far away the star is. Because light spreads out and thins as it travels, a bright star far away and a faint star nearby can send us the very same amount of light. So without the distance, the size stays hidden. And measuring the distance to a lone neutron star drifting by itself in the dark is one of the hardest measurements in all of astronomy. There is one great and trusted way to measure distance, and it is worth pausing on because it is beautiful in its simplicity, and it is the foundation on which almost everything else is built. Hold up one finger at arm's length. Close one eye, then the other, back and forth. Watch your finger jump against the far wall. It jumps because your two eyes look at it from slightly different places, and the nearer a thing is, the more it jumps. Now the Earth, as it circles the Sun across a year, is like a great slow eye that moves from one side of its path to the other. And so a nearby star, watched patiently across the seasons, appears to shift ever so slightly against the far more distant stars behind it, first leaning a little one way, then the other, as the Earth swings from one side of its orbit to the far side. The size of that tiny yearly shift tells us the distance by nothing more than patient geometry, the same geometry a surveyor uses to measure across a river he cannot cross. Astronomers call this shift parallax, and it is the first rung on the whole ladder by which we measure the universe. For a lone neutron star, the shift is achingly small because the star is so far, but with careful watching across years it can sometimes be caught, and when it is, the distance falls into our hands, and with the distance, at last, the size. Now let me tell you about one particular star, because its story shows both the promise and the difficulty of everything we have been describing, and because, for a time, it was the brightest hope that a quark star might really be out there. Carries a plain catalogue name, a string of letters and numbers, the kind of name astronomers give to a point of light before it has earned a friendlier one. It is a lone neutron star, not far away as these things go, one of the nearest to us that we know, close enough that its faint glow can be studied with real care. And when astronomers measured its light, its temperature and the flood of it, and worked out its distance, and put all of it together to find its size, they got a number that made them sit up. The star seemed too small. Its glowing surface, by their best reckoning, seemed to be only about 5 or 6 miles across in radius, smaller than any neutron star should be able to be, too small for even the stiffest ordinary neutron matter to explain. And a star too small for neutron matter is exactly what a quark star should look like. Denser matter, packed into a smaller ball. For a while, this quiet, nearby point of light was held up as perhaps the best candidate we had, the strongest single case that somewhere out there matter had been crushed past the neutron into something stranger. Papers were written asking the question plainly in their very titles. Was this a bare quark star, or only a naked neutron star wearing a puzzling face? But here is the honest ending of that particular story, and it teaches the lesson of the whole night. The measurement was not certain. The size we read from a star's glow depends on things we cannot fully pin down, on the exact distance, which is hard to measure, and on the fine details of how the star's surface gives off its light, which may not be as simple as a plain warm glow. Perhaps the star only appears to glow from a small hot patch on its surface, rather than all over, and if so, our reading of its size would be thrown off. As the measurements were refined and refined again across the years, the case grew softer, less sure. Today we cannot say that this star is a quark star. We can only say that it once looked small enough to be one, and that we still cannot fully explain it, and that it remains, quietly, one of the puzzles we have not put to rest. It is not proof. But it is a hint, one of several hints, that keep the question alive. So that is one path to a quark star, through the measure of size, the search for a star too small for its weight. But there is another path entirely, a second clue that does not depend on measuring size at all, and it is just as clever. Depends on watching how these stars cool, how they slowly give up the terrible heat of their birth over the long ages, because it turns out that matter made of free quarks would cool in a different way, faster than ordinary neutron matter, and if we could catch a star cooling too quickly, that too would betray something strange hidden inside it. So let us follow that second path now, the path of the cooling star, and let us meet another candidate, one born from a fire that human eyes actually witnessed long ago and wrote down. To understand the clue of the cooling, we have to think for a moment about how a hot thing loses its heat, and then about how a neutron star and a quark star would each do it differently. A cup of tea left on the table cools by giving its warmth to the air around it. A neutron star has no air around it, only the emptiness of space, and so it cannot cool that way. Instead, it cools in two deeper ways. Part of its warmth leaks away as light, the faint glow we spoke of. But there is another way, a hidden way, and it is by far the most important in the early life of one of these stars. The star cools by giving off ghostly particles called neutrinos. A neutrino is one of the strangest and shyest things in all of nature. It is a tiny particle, so light and so aloof that it can pass through solid matter almost as though the matter were not there at all. Neutrinos are streaming through you right now, uncountable numbers of them, pouring out of the sun and passing through your body and the whole earth without so much as a nudge. They almost never touch anything. And because they almost never touch anything, when they are made deep inside a hot dense star, they do not get trapped and bounced about the way light does. They simply fly straight out, carrying their little bundle of heat away with them into the dark, leaving at once. So the more freely and the more quickly a star can make neutrinos in its core, the faster it cools, because each neutrino is a small thief of warmth that escapes without paying any toll. Now here is the heart of the second clue. Matter made of free deconfined quarks can make neutrinos far more easily and far more quickly than ordinary neutron matter can. In a sea of free quarks, there are fast and easy ways for the quarks to shed neutrinos, ways that are largely forbidden or slowed down inside ordinary neutron matter. So a quark star, or a neutron star with a quark heart, would cool faster, sometimes far faster, than a plain neutron star of the same age. If we could find two stars of the same age, and one of them had grown far colder than the other, colder than any ordinary neutron star has any business being, then that cold star would be whispering to us that something inside it is shedding heat too quickly, that its heart may be made of stranger stuff. The cold itself would be the clue. To use this clue, we need to know a star's age, and knowing the age of a star is usually just as hard as knowing its distance or its size. Except, once in a great while, nature hands us a gift. Once in a great while, a star was seen to die by human eyes, and the moment was written down, and the record has come down to us across the centuries. And when that happens, we know the exact age of the neutron star left behind, because we know the very year its parent star exploded. There is one such star at the heart of a cloud of glowing wreckage, the remains of a supernova whose light reached the Earth long ago, in the 12th century, when it was noted and recorded by careful watchers of the sky in the year 1181. We know, therefore, almost exactly how old the neutron star at its center is. It has been cooling, out in the dark, for something like 8.5 centuries, a span we can count. And when astronomers turned their X-ray telescopes on that star, on the small warm point at the center of that ancient wreckage, they found something that made them pause. It was too cold. For its known age, it had cooled further than the ordinary models of neutron matter said it should have. It had shed its birth heat too quickly, arriving at a chill that plain neutron matter struggles to explain. And a star that has cooled too fast is exactly what the quark idea predicts, because the free quarks in its heart would have been carrying heat away, all those centuries, faster than neutrons ever could. So here was a second kind of hint, from a completely different direction than the first, pointing toward the same strange possibility. Not a star too small this time, but a star too cold. And yet, once again, I must give you the honest ending. because honesty is the truest comfort I can offer on a night like this. Cold of that star is not proof either. There are other ways a neutron star might cool faster than the simplest models expect, other exotic processes that do not require free quarks at all, other kinds of matter that might do the same job. The measurement is real. The star does seem too cold, but it does not force us to conclude that quarks are the answer. It only leaves the door open. It only says, again perhaps. And so we have two candidates now, two puzzles, one a star too small and one a star too cold, and neither one seals the case, and both keep the question warm and alive. I want you to notice something about all of this, something quiet and rather beautiful, before we move on. Every path to the quark star is indirect. We never see the quarks. We cannot. They are locked away inside these stars, or crushed into a form we can only reason about from afar. We catch them only by their shadows, by a star that is a little too small, or a little too cold, or a little too heavy, or a little too something, a small wrongness that the ordinary picture cannot quite account for. We are like people standing at the edge of a dark wood who never see the animal that lives within, but who read its presence from a bent branch here, a print in the mud there, a sound in the night. We infer. We reason. We hold the shape of the unseen thing in our minds, built up from a scattering of faint clues. And there is a kind of humility in that, a proper smallness, that seems fitting when we are speaking of the densest matter in all creation. Now there is a deeper layer to the puzzle of the cooling, one more idea I want to bring in gently, because it shows how strange this matter might truly be, and because it has one of the loveliest names in all of physics. Down in the crush of a quark star, the free quarks might do something unexpected. They might pair up. Under the right conditions, quarks that are near one another can join into pairs, and when a whole sea of them pairs up together in step, the matter takes on a new and orderly state, a state that flows and behaves in ways that are deeply strange. Physicists call this state color superconductivity, borrowing the word superconductivity from a related marvel we have made here on Earth, where certain metals, chilled to a great cold, let electricity flow through them without any resistance at all, forever, as though the wire had forgotten how to push back. In a color superconducting quark star, the paired quarks would settle into a state so orderly that it changes how the star cools, how it responds to being squeezed, how it behaves in nearly every way. There are even different flavors of this pairing, different patterns the quarks can fall into depending on how dense and how cold the matter is. In one pattern, only two of the kinds of quark manage to pair, while the heavier strange quark, being more sluggish, is left out of the dance. In another, deeper and more orderly pattern, all three kinds join together in a single locked arrangement, so symmetric and so complete that it has a name of its own, a name that speaks of the colors and the flavors of the quarks, all bound together in perfect step. We do not know whether any real star holds matter in these states. The fact that our equations allow them, that the densest matter might arrange itself into such quiet and orderly and unearthly patterns, is one more reason this question has held the attention of so many careful minds for so long. The deeper we look, the stranger and the more delicate the possibilities become. There is one more way of measuring these hidden stars, and it is the newest of them all, and to my mind the most astonishing, because it does not use light at all. For all of human history, every single thing we ever learned about the sky came to us on light, on some form of it, whether the light our eyes can see, or the X-rays and radio waves our machines can catch. Light was the only messenger. And then, within the last decade or so, we learned to listen to the sky in an entirely new way, not with light, but with ripples in the fabric of space itself. To feel this, we have to step back for a moment and think about what space is and how it can carry a wave. We are used to thinking of space as a mere emptiness, a nothing, a stage on which things happen. But one of the deepest truths we have learned is that space is not a passive nothing. It can bend. It can stretch. It has a kind of give to it, a flexibility, and heavy things curving it are what we feel as gravity in the first place. The Earth circles the Sun, not because a rope ties them together, but because the Sun's great mass bends the space around it into a kind of valley, and the Earth rolls around the inside of that valley like a marble circling a bowl. Space is a fabric, and mass warps it. That is gravity, in the deepest telling we have. And here is the wonderful consequence. If space is a fabric that can bend, then it can also ripple. If you take two very heavy things and swing them around each other hard and fast, they stir the fabric of space and send waves of stretching and squeezing rippling outward across the universe at the speed of light, like the ripples that spread when you swirl your hand in still water. These are gravitational waves. As one passes through you, it very slightly stretches you in one direction and squeezes you in another, and then the other way around, over and over, though by an amount so unthinkably tiny that no one felt them for 100 years after they were first predicted. To catch them, we had to build some of the most sensitive machines ever made, machines that can measure a change in length smaller than a fraction of the width of a single one of the tiny particles inside an atom, across instruments miles long. It is one of the great feats of patient human hands, and it opened a wholly new sense with which to feel the sky. Now think about what makes the strongest ripples. Two very heavy things swung very fast and very close. And there are few things in the universe heavier or more compact than neutron stars. So imagine two neutron stars, born as partners, circling one another for ages, slowly drawing closer as they stir the fabric of space and lose a little energy to the ripples they make. Across millions of years they spiral inward, closer and closer, faster and faster, until in their last moments they are whirling around each other hundreds of times a second, almost touching, before they finally crash together in a single violent instant. That final in-spiral and collision sends out a rising song of gravitational waves, a chirp that climbs in pitch and grows louder and louder until the moment of the crash. And in the year 2017, for the first time, we heard exactly such a song. Two neutron stars in a galaxy far from our own had spiraled together and collided, and the ripples from that collision, after travelling across space for 130 million years, washed over the Earth and set our instruments ringing. And this time, unlike the black hole collisions we had heard before, there was also light. Telescopes around the world swung toward the place in the sky the ripples came from, and there they caught the glow of the aftermath, a fading fire kindled by the collision, in which, we believe, a great deal of the gold and the silver and the heavy metals of the universe were forged in a single instant and flung out into space. It was the first time we ever felt an event with gravitational waves and saw it with light at the same time, the opening of a new kind of astronomy where we both hear and see the sky together. And this single event, this one collision, heard and seen, told us a great deal about our question. Because the exact shape of the rising song, the precise way the pitch climbed in those final moments, depended on how the two neutron stars pulled and stretched one another as they drew close. A star made of stiff, hard matter holds its shape stubbornly, even under the fierce pull of a close companion. A star made of softer, more yielding matter stretches and deforms more easily. And that difference, that stretching, left its fingerprint on the song. So by listening carefully to the exact shape of the chirp, physicists could read something about the stiffness of the matter inside those stars, about the very equation of state we have been chasing all night. The collision was, in effect, a laboratory we could never build, an experiment nature ran for us in the deep dark, squeezing neutron star matter and letting us watch how it responded. What the song told us was that the matter is neither too soft nor too stiff, but somewhere in a middle range. It ruled out the softest possibilities, and it leaned against the very stiffest ones too, and it helped pin down how large a neutron star of a given weight should be, narrowing the numbers we had struggled with for so long. It also spoke to the great limit, the last fence at the edge of the cliff, the greatest weight a star can bear before becoming a black hole. From the way the collision played out, from what became of the wreckage in the moments after the crash, physicists reasoned that the limit sits at around 2 1/10 or so times the mass of the Sun, perhaps a little more, tightening our estimate of that crucial number as never before. And every time that number is tightened, the window for the quark star shifts and narrows with it. Remember that the quark star, if it exists, lives in that narrow band of weight just below the final limit, in the gap left open if the matter is soft enough. So each new measurement, each collision heard, each heavy pulsar weighed, each cooling star studied, presses in on that window from one side or another, making it a little smaller, a little better defined. We have not closed it. We have not proven the quark star is real, and we have not proven it is impossible. But we have drawn the walls of its possible home closer and closer, tightening our gentle net around a thing we have never seen, waiting patiently for the one measurement that might finally settle it. That is where the science stands tonight, honestly, poised at the edge, the question still open, the net still empty, but drawn tighter than ever before. And now, before we turn toward what all of this might mean for us, there is one more idea I want to share with you, the wildest of them all, because it takes everything we have spoken of and imagines it happening not slowly and quietly, but all at once in a single catastrophic flash. It is the idea that a neutron star might not become a quark star gently over the ages, but might convert in an instant, in an explosion of a kind we have imagined but never confirmed, an event so violent it might be among the brightest things the universe can produce. It even has a name. Let us turn to it now, gently, and then we will begin the long, slow descent toward rest. Imagine a neutron star sitting quietly in the dark, right at the edge of what it can bear. Perhaps it was born heavy. Perhaps it has a companion, and has been slowly pulling matter off that companion for ages, growing heavier with each passing century, like a bucket filling drop by drop. And imagine that at last it crosses some hidden threshold, gains that final ounce of weight, and the neutrons at its heart can hold on no longer. In the plainest telling, the neutrons in the core begin to dissolve into free quark. But here is the wild thought. What if that dissolving, once it begins, does not stay politely in the core? What if it spreads? Remember the strange matter idea, the notion that strange quark matter might be more stable than ordinary matter, a deeper valley that ordinary matter would fall into if only it could find the road. Now imagine that in the crushed heart of this overloaded neutron star, a first tiny seed of strange matter forms. And imagine that this seed, being a lower and more restful state, begins to convert the matter around it, touching the neutron matter next to it and pulling it down into the deeper valley too, which in turn touches the matter beyond it, and so on, a change that spreads outward through the star like a flame racing through dry grass, or like a crystal spreading through a liquid that was poised and ready to freeze. In a fraction of a heartbeat, the whole star, or a great part of it, might convert from neutron matter into quark matter, tumbling all at once into that deeper valley. And when matter falls into a deeper valley, it gives up energy, just as a ball rolling downhill gives up energy. And here the drop is so deep, and the amount of matter so vast, that the energy released would be staggering beyond easy telling. A physicist named Rachid Ouyed, working in Canada together with colleagues, gave this imagined event a name in the early 2000s. They called it a quark-nova. Not a supernova, the death of a great star that we know and have seen many times, but a second explosion that might follow it, the violent conversion of the neutron star left behind into a quark star, a separate flash, perhaps days or weeks or longer after the first. The energy such an event might release is hard to hold in the mind. By some estimates, a quark-nova could pour out an amount of energy that rivals the great supernova that made the neutron star in the first place, a second death following the first. And this has led to a fascinating possibility, still only an idea, still unconfirmed, but a lovely one to turn over. Perhaps some of the brightest and strangest explosions we see in the distant universe, explosions that seem too bright for an ordinary supernova to explain, the ones we sometimes call superluminous, are not ordinary supernovae at all, but supernovae followed by a second quark-nova flash, the two deaths together pouring out more light than either could alone. And perhaps some of the sudden, brief, enormously powerful bursts of high-energy light we catch flashing across the sky, the ones we call gamma-ray bursts, among the most violent events known, might in some cases be the signature of a neutron star converting in an instant into something denser and stranger. I want to be very careful and very honest here, more careful even than usual, because this is the most speculative idea of the whole night. The quark-nova has never been confirmed. It is a model, a possibility, one explanation among several, for events that have other proposed explanations too. Many careful scientists doubt it, may be entirely wrong. I share it with you not because it is established truth, but because it shows how far the consequences of our simple question can reach. If quark stars exist, and if matter can convert into them, then that conversion might light up the distant universe in some of the most dramatic ways we have ever witnessed, and events we have puzzled over for years might have this strange transformation hidden at their heart. The question of what comes after the neutron is not a small or an idle one. It reaches all the way out to the brightest fires in the sky. And so we arrive at the place I have been promising you all night, the moment to be fully and gently honest about where we stand, because that honesty is not a disappointment. It is, I think, the most peaceful part of the whole story. Let me gather it all together for you now, softly, the way you might gather up the last warm coals of a fire before bed. We do not know if quark stars exist. That is the plain truth of it. After more than 50 years of thinking, after the finest telescopes and the most sensitive instruments ever built, after weighing pulsars and measuring the glow of lone stars and timing the cooling of ancient remnants and listening to the ripples of colliding stars across 130 million years, we still cannot say with certainty that a single quark star is out there. Every candidate has faded into maybe. Every clue has stayed a hint. The equation of state, the stiffness of the densest matter, remains not fully known, and until we know it, the door stays ajar, neither open nor shut. It is entirely possible that quark stars are common, scattered through the galaxy, hiding in plain sight among the neutron stars we have already catalogued, and we simply cannot yet tell them apart. And it is entirely possible that they do not exist at all, that neutron matter holds the line all the way to the black hole, and that the quark star was only ever a beautiful idea that nature declined to build. I find, and I hope you will find too, that there is something deeply restful in that not knowing. We live in a time that is impatient with mystery, that wants every question answered by morning, that treats not knowing as a kind of failure to be hurried past. The not knowing here is not a failure. It is an honest measure of how deep the universe runs, how far past the edge of our reach its strangeness extends. Somewhere out there tonight, while you lie warm beneath your blanket, there may be a star only 12 miles across, heavier than the sun, made of matter that has forgotten how to be atoms, a sea of naked quarks bound by the strongest force there is, spinning slowly in the dark, keeping it secret. Or there may not. Both of these can be true at once, held gently side by side, and neither one needs to be settled tonight for you to rest. The mystery is not a problem to be solved before you sleep. It is a vastness to be rested within. And that is where I would like to take you now, away from the hard edges of the science, into the wider and softer meaning of it all, into what it might mean for you, small and warm and breathing, to share a universe with such things. Before we leave the science behind entirely, I want to spend a little longer in that quiet workshop of measurement, because there is still more patient cleverness to admire there, and admiring it is a restful thing in itself. We have weighed these stars by watching them dance with a partner. We have measured their size by reading the temperature and the flood of their glow. We have felt their matter stretch by listening to the ripples of their collisions. But there is another way we are learning to measure their size now, and it is so delicate and so ingenious that it is worth resting on. Many neutron stars, as we said, are not smooth all over in their warmth. They have hot spots, patches on their surface that glow more brightly than the rest, often near the places where their great magnetic fields funnel matter down onto the crust. And because the star is spinning, those hot spots sweep past our line of sight, around and around, hundreds of times a second, so that the total light we receive rises and falls in a steady rhythm as the bright patch turns toward us and then away. Now here is the beautiful part, the part that borders on the unbelievable. A neutron star is so dense and its gravity so strong that it bends the very path of light near its surface. Light leaving the far side of the star, light that by all ordinary reckoning should be hidden from us behind the bulk of the star, is bent around the curve of that intense gravity and brought partway toward us, so that we can see a little way around the back of the star, as though it were slightly transparent at the edges. And exactly how much the light is bent depends on how compact the star is, on the balance of its mass and its size. So by watching, with exquisite care, the precise rhythm of the rising and falling light as a hot spot sweeps around, and by measuring how the shape of that rhythm is distorted by the bending of the light, physicists can work backward to the star's size. We measure the width of a thing 12 miles across, thousands of light years away, by watching how its own gravity bends its own light around its own back. If that does not fill you with a quiet wonder, I am not sure what could. Instruments built to do exactly this, to time the flickering X-ray light of spinning neutron stars with astonishing precision, have begun to pin down the sizes of these stars better than ever before. And each measurement, again, presses on our question. The neutron star, measured to be a little larger than expected, argues for stiffer matter and against a quark core. A star, measured to be surprisingly small, keeps the stranger possibilities alive. Slowly, star by star, a picture is being built. A chart on which each measured star is a single point, its weight along one direction and its size along another, and the shape that all those points make together will one day reveal the equation of state, and with it the answer to whether the quark star has a home in the real universe or only in our equations. We are filling in that chart now, point by patient point, one star at a time. It is unfinished, but it is being drawn in our own lifetimes by human hand. And what would it take truly to settle the question once and for all? What would a real, undeniable quark star look like, caught at last? Might be a star measured so small for its weight that no possible neutron matter, however stiff, could account for it, a star that simply cannot be anything but denser stuff. Might be the catching of a quark-nova in the act, a second flash after a supernova, with just the signature the models predict. Might come from the ripples of a collision so precisely measured that the softness of the matter can only mean quarks have come unbound. Or it might come from something we have not yet thought of, some new messenger, some new instrument, some clue we cannot now imagine, the way no one, a century ago, could have imagined listening to the sky through ripples in space itself. The history of this question is a history of surprises, of doors opening where we did not know there were walls. Would be a strange arrogance to think we have found the last door. There is even the faint, wild possibility that a piece of a quark star might one day be found much closer to home. Remember those imagined chips of strange matter, the strange nuggets that might in theory drift through space, small and dark and unthinkably dense. If they exist, one might occasionally strike the Earth or pass through it and leave some faint trace, a peculiar track, a tiny quake, a signal unlike anything ordinary matter could make. People have searched for such traces in old rocks, in sensitive detectors, in the records of the great arrays we build to catch cosmic rays. Nothing certain has ever been found. The search goes on, quietly, another patient net cast into the dark. And is there not something wonderful in that? That the answer to a question about the densest stars in the sky might, just possibly, be resting in a stone, or falling through the night air above you even now, too small and too strange to notice. I have told you all of this, all these clever ways of reaching across the dark, for a reason that goes beyond the quark star itself. I have told you because I think it is one of the most quietly beautiful things about being alive at this moment in the long story of our kind. We are soft creatures, you and I. We live briefly. We are bound to one small, warm world, and we cannot travel to these stars, cannot touch them, cannot bring even a grain of them home to study. By every ordinary measure, they should be utterly beyond us, forever unknowable, mere points of light with all their secrets sealed. And yet, through patience, through cleverness, through the slow gathering of faint clues across generations, we have reached out and taken the measure of them anyway. We have weighed things we cannot see. We have sized things we cannot resolve. We have felt the stiffness of matter no hand will ever hold. It is one of the gentlest and grandest things our kind has ever done, and it was done not by any single person, but by many, patiently, each adding a little to what the last had found, a long relay of curiosity handed down across the years. When you consider it that way, the search for the quark star is not really a story about stars at all. It is a story about us, about what we are, about the strange and lovely fact that a small, warm mind resting in the dark can wonder about the heaviest matter in creation and slowly, patiently begin to know it. And that thought is the doorway into the last and softest part of our night together. For if we can reach so far outward into the crushed hearts of dying stars, then it is worth turning the wonder back around, gently, and asking what all of it means for you, lying here, breathing slowly, held by the same forces, and made of the same ancient stuff. Let us step now out of the workshop of measurement and into that wider quiet, and let the numbers soften into meaning, and the meaning soften into rest. Let us rest for a while with the scale of the thing, because the scale is where the wonder lives, and returning to it, turning it slowly in the mind, is itself a kind of quiet the body knows how to sink into. I am going to say the size of a quark star to you again, several times, in several different ways, not because you have forgotten it, but because some things are worth saying more than once, the way you might look at the sea again and again without ever being done with it. Quark star, if it exists, holds more than the whole mass of our sun inside a ball, perhaps 12 or 14 miles across. Let that settle. Take the sun, that furnace so vast that 1,000,000 Earths could be poured inside it and still leave room. Take a sun and a half of matter, or nearly 2 suns, and fold all of it, without losing a single grain, into something the size of a town you could walk across between one meal and the next. That is the first way to hold it. Here is another way. Think of a mountain, a great grey mountain, the kind that takes half a day to climb and fills the whole sky when you stand at its foot. Now imagine that the matter of that entire mountain has been squeezed down until it would sit in the bowl of a single teaspoon, the small spoon you might stir into a warm drink. One spoonful, as heavy as a mountain. And a quark star is not one spoonful of such matter. It is a whole world of it, town-sized, every teaspoon of it heavier than a mountain, all of it packed together and turning slowly in the dark. Here is another way still. Picture the distance from where you lie now to the nearest large city, a drive of an hour or two along a dark road. That, more or less, is the whole width of the star. And into that small span is folded more matter than sits in the entire sun, whose light takes your eye and fills the whole of a summer day, whose warmth you feel on your skin from 93 million miles away. All of that and more in the span of a short drive. The mind reaches for the picture and slides off it, and that is all right. It is meant to be too large to hold. You are not failing to grasp it. You are only standing at the edge of something that is genuinely larger than grasping, and the right response to that is not strain, but a kind of soft surrender, a letting the vastness be vast. And think of what holds it together. Not a shell, not a wall, not any container. If it is a pure strange star, then it is held by the strong force itself, the same force that binds the 3 quarks inside a single neutron in your own body, now stretched to bind an entire star, quark to quark, across a whole town-sized world of them, without any container at all, a single lump of the strongest bound matter there is. The very same force that lives inside the smallest piece of you, holding an entire star together in the dark. There is a strange kinship in that, if you let yourself feel it. The force that makes you solid, that keeps the little cores of your atoms from flying apart, is the same force that might, somewhere out there, be holding a star together with no help from gravity at all. Now let us set the quark star back on its staircase one more time, and walk the whole descent again, slowly, because seeing the whole ladder at once is its own kind of peace. At the top, ordinary matter, mostly empty space, gentle and familiar, the matter of your hand and your pillow. One step down, the white dwarf, a whole sun folded into the size of the earth, a spoonful as heavy as a truck. One step further, the neutron star, a sun and a half folded into a town, a spoonful as heavy as a mountain, held up by the stubbornness of neutrons that refuse to share a room. One step further still, uncertain, perhaps real and perhaps only imagined, the quark star, denser yet, the neutrons themselves dissolved into a sea of free quarks, matter crushed to the very last form it can take and still be matter at all. And then the final step, the black hole, where the staircase ends, where matter falls away past every limit and even light cannot climb back out, and where our knowledge, honestly, ends too. The quark star lives on that second to last step, right at the edge, in the narrowest of margins between the strangest thing we understand and the thing we do not understand at all. It sits, if it sits anywhere, in the last thin band of the knowable, just before the door closes on knowledge entirely. And there is something fitting in that, something almost gentle, that the densest matter that can still be studied, still be reasoned about, still wear a face we might one day read, should live right there at the frontier, one step short of the dark that swallows everything, including our understanding. It is as far as we can go and still be looking at a thing rather than at a mystery with no bottom. It is the last landing before the fall. And when you hold all of that, the whole staircase, the whole descent from your soft familiar world down to the edge of the black hole, something curious happens to your sense of your own place. You begin to feel where you stand on that staircase. You stand at the very top, on the gentlest step in the realm of ordinary matter, of empty space and quiet forces, of warmth and softness and breath. You are made of the lightest, airiest, most spacious kind of matter there is, matter so full of emptiness that it is a wonder it holds together at all. And far below you, down the long descent, lie these crushed and cooling remnants, these town-sized weights, these seas of naked quarks, the matter of the deep. You and they are made of the same ultimate ingredients, the same quarks, the same forces. You are simply arranged more gently, spread out more kindly, given more room to be. And that, too, is a thing worth resting in, that of all the ways matter can be arranged in this universe, from the crushed heart of a quark star to the gentle sprawl of a living body. You have been given one of the rare and airy and spacious arrangements, the kind that can wonder, the kind that can rest, the kind that can lie in the dark and think about the stars. Let us do something gentle now before we turn toward what all of this means. Let us imagine, softly and without any fear, what it might be like to draw near one of these objects, not to land on it, for nothing could ever land on it and remain a thing with a shape, but only to approach it in the mind, to picture it the way you might picture a place you will never go, simply for the quiet pleasure of imagining. This is only a picture. You are safe here in your bed. But let us go there together in the mind alone and look. Picture yourself drifting through the dark, far out toward a faint point of light that grows slowly as you approach. First, it seems like any distant star, small and cool and unremarkable. But as you draw nearer, you begin to sense that something is wrong with the space around it, that the light of the stars behind it is being bent and smeared, gathered into strange arcs and rings, as though you were looking at the far stars through a lens of curved glass. That is the star's gravity, so strong that it bends the very path of light, warping the view of everything behind it into a shifting halo. You have not even reached the star, and already it is reshaping the sky. Nearer still, and the star resolves at last into its true form, a tiny, fierce, glowing ball, no wider than a town, blazing softly in a light your eyes could not quite see, turning, perhaps, faster than you could follow, whipping around many times in a single second. And around it, that strange bending of light grows stronger and stranger, so that you can see, impossibly, a little way around the back of the star, its far side brought partway into view by the curving of its own light around its own gravity. It is as though the star were slightly transparent at its edges, showing you more of itself than should be possible, a thing that breaks the ordinary rules of seeing. And you would feel it long before you reached it. Pull of its gravity would reach out and take hold of you, and because your near side would be pulled so much harder than your far side, you would feel yourself being stretched, gently at first, then not gently at all, drawn out long and thin toward that fierce small point. Nothing soft could survive that stretching. Nothing with a shape could keep it. The star would not need to touch you to unmake you. Its gravity alone, reaching out across the empty space, would be enough. And so we stop here, at a safe distance, in the mind, and only look and marvel and come no closer. But hold the picture a moment longer, because there is a beauty in it that outlasts the danger. This tiny, fierce, impossible thing, this town-sized weight heavier than the sun, bending light around itself, stretching space, turning in the dark, is one of the strangest and most extreme objects the universe knows how to make. And if it is a quark star, then its very surface, if it has one, would be like nothing else in all creation, a sharp and sudden wall of pure quark matter, a boundary only a hair's breadth below which lies matter crushed past the neutron into a naked sea of quarks, and above which lies nothing but empty space. A bare surface of the deepest matter there is, gleaming faintly in the dark, keeping its ancient secret, turning quietly, asking nothing of anyone. To have seen it, even in the mind, even from a safe and distant remove, is to have looked upon one of the true wonders of the cosmos. a thing at the very edge of what matter can be. And now we may let the picture fade softly and draw back from that fierce small point and return to the warmth and the safety of the dark around you, carrying only the wonder of it and none of the danger back with us into the quiet. So let us ask softly what a quark star has to do with you at all. It is so far away. It is so strange. May not even exist. What could such a thing possibly have to do with a warm body lying in a bed on an ordinary evening with the small and gentle business of a human life? And yet I think the connection is real and deep and worth resting in, and I would like to draw it out slowly for you now. Begin with this. The very atoms that make up your body, the iron in your blood, the calcium in your bones, the carbon that forms the frame of every living cell in you, were not made on Earth. They were made inside stars. Every atom in you, heavier than the lightest few, was forged in the hot heart of some star that lived and died long before the sun was born. Carbon and the oxygen were cooked slowly in the cores of stars across their long lives. And the heaviest elements, the iron in your blood among them, were forged in the very fires we have been speaking of all night, in the death throes of great stars, in the core collapse supernovae that leave neutron stars behind, and in the collisions of neutron stars themselves, those same collisions whose ripples we now catch across 130 million years of space. Think of that for a moment. The gold that a person might wear on a finger, the silver, the heavy and precious metals, we now believe a great deal of it was made in exactly the kind of neutron star collision we heard and saw in the year 2017. Two dead stars crashing together and flinging newly forged treasure out into the dark. The same events that press upon our question of the quark star, the same crushed and dying stars we have spent this whole night trying to understand, are the forges in which the stuff of you was made. You are not separate from these things. You are made from their leftovers. You are, quite literally, the cooled and gentled ash of ancient stellar fires, gathered up over billions of years and arranged somehow into a thing that can lie in the dark and wonder about the fires it came from. And the iron especially, the iron we spoke of long ago tonight, the ash at the end of a star's fire, the most contented nucleus there is, the very element whose stability the strange matter idea dares to challenge. That iron runs in your blood. It is what lets your blood carry the breath from your lungs to every corner of your body, the quiet chemistry that keeps you alive from one moment to the next. The same iron that ends a star's life, that triggers the collapse that makes a neutron star, that might, if the boldest ideas are right, be dethroned as the true resting place of matter by the strange stuff of a quark star, is the iron that is, right now, carrying oxygen through you as you breathe slowly and grow heavy towards sleep. The story of the quark star and the story of your own body are told in the same handful of ingredients. They are not two stories. They are one. So when we ask what comes after the neutron, when we wonder whether matter can be crushed past the neutron into a sea of free quarks, We are asking a question about the deepest nature of the very stuff we are made of. We are asking how far our own ingredients can be pushed, what shapes they can take at the far edge of possibility, what the ultimate ground state of matter truly is, the deepest and most restful form that all things, given enough time and enough pressure, would settle into. And you are made of that matter. The question is, in the end, a question about ourselves, asked at the largest possible scale. Now let us widen the view further and think for a moment about time, because the quark star lives not only at the edge of density, but at the edge of deep time, and dwelling on deep time is one of the oldest ways the mind has of finding peace. When you look up at the stars, you are not seeing them as they are. You are seeing them as they were, each one at the moment its light set out toward you. The nearest bright stars you can see with your unaided eye show you light that left them years or decades ago. Some of the stars in the familiar patterns of the sky are showing you light that began its journey centuries ago, before your grandparents' grandparents were born. And the faint smudges of distant galaxies, if you are somewhere dark enough to see them, are showing you light that left them before they were human beings at all, before there was anything on Earth that could look up. The neutron stars we study, the collisions we hear, are often thousands or millions of light years away, which means the light and the ripples we catch tonight set out long, long before this moment. When you consider that the collision we felt in 2017 actually happened 130 million years ago, that the two stars crashed together when the earliest flowers were only beginning to appear on Earth, and that their message has been crossing the dark ever since, patiently, at the speed of light, arriving at our small world only now, only in our brief moment, only to be caught by instruments we finished building just in time, you begin to feel the strange grace of it. We are catching messages sent before we existed, by objects that may no longer exist, across spans of time that make a human life seem no longer than a single breath. And somehow that does not diminish the breath. Somehow it makes each breath feel more precious, more improbable, more worth taking slowly and gratefully in the quiet of the night. For consider how brief you are against all of this. A star like the sun lives for many billions of years. A neutron star, once formed, may cool slowly for far longer than that, drifting on and on into a future so distant we have no real way to feel it. And here you are, given a handful of decades, a small warm span of years, in which to be awake and to wonder. It would be easy to feel small in the shadow of all that time, small and fleeting and unimportant. But I would ask you to feel it differently tonight. Of all the vast reaches of time, all the billions of years before you and the billions that will follow, you have been given this one small stretch in which to be here, to breathe, to look up, to wonder about quark stars in the dark. The universe spent almost all of its long history without you, and will spend almost all of its long future without you. And yet here, now, in this narrow and precious window, you exist, and you are awake, and you are able to hold in your soft and temporary mind a thought about the densest matter in all creation. That is not smallness. That is a rare and fleeting gift, a brief opening of a window that was closed for ages and will close again, and you are here for it, now, tonight. And there is a rest in that, if you let there be. You do not have to solve the quark star. You do not have to understand it fully, or prove it exists, or hold every number of it in your mind. You have only to be here, briefly, in the warm and spacious matter of a living body, sharing a universe with such wonders, awake for a little while in the long night of time. The stars will go on with their slow and enormous lives, being born and dying and crushing themselves into strange forms, whether or not you understand them, whether or not you are watching. And you may lay all of that down now, gently, the way you would lay down a heavy pack at the end of a long walk, and simply rest in the fact of it, in the sheer improbable gift of being here at all, of being made of star stuff arranged into something that can wonder, for this one brief and precious while. Let us stay here now, in this softer place, and let the hard edges of the science drift a little further off, the way the shore drifts away when you lie back in still water and let it hold you. We have done the thinking. We have walked all the way down the staircase and back up again. We have weighed the unweighable and measured the unmeasurable, and stood at the edge of the knowable and looked out into the dark beyond it. Now there is nothing left to solve, and nothing left to do but rest in what we have seen, and let it carry us gently towards sleep. I have been thinking, as we talked tonight, about how strange it is that a thing so violent and so extreme as a quark star should be, in the end, so quiet. Consider it. It is born in one of the most violent events the universe can produce, the collapse and explosion of a great star, a blast that for weeks can outshine a whole galaxy. It is made of matter crushed past every ordinary limit, matter under a pressure we cannot begin to reproduce, matter at the very edge of what physics allows. And yet, once it is made, once the fire has faded and the wreckage has drifted away, it simply hangs there in the dark, quiet as a held breath, giving off almost no light, turning slowly, keeping its secret, doing nothing at all but existing for ages upon ages, longer than we can easily imagine. The most extreme matter in creation, resting in perfect stillness. There is something in that I find deeply consoling, and I hope you do too. That even the most violent births settle, in time, into stillness. That even the most crushing pressures come to rest. That after every storm, however great, there is a long, quiet keeping. And I think about how these stars keep their secrets so gently. They do not hide from us out of any wish to hide. They are simply far away, and small, and quiet, and made of stuff we cannot reach. Their mystery is not a locked door slammed in our faces. It is more like the mystery of a deep forest at night, or the bottom of the sea, or the inside of another person's mind, a mystery that is not cruel, only vast, only deeper than our reach, and patient with our slow attempts to know it. There is no unkindness in a universe that keeps some of its secrets. There is, if anything, a kind of generosity in it, that it should be so much larger than our understanding, that no matter how far we reach, there is always more, that we will never, in all our long history, come to the end of things to wonder about. A universe we had fully solved would be a smaller and a lonelier place. The not knowing is not a wall around us. It is a horizon that keeps receding as we walk toward it, always giving us somewhere further to go. Think of all the people, across all the years, who have lain as you are lying now, and looked up and wondered. Long before anyone knew what a star was, before anyone dreamed of atoms or quarks, or the crushing hearts of dying suns, people lay in the dark and looked up at those same points of light, and felt the same thing you feel, that quiet ache of wonder, that sense of being small beneath something vast. They did not know what they were looking at. They made up stories to hold the sky together, patterns and names and tales passed down around fires. And we, tonight, know a great deal more than they did. We know the stars are suns. We know some of them have died and left behind these strange crushed remnants. We know how to weigh them and measure them and hear their collisions. And yet the feeling, the essential feeling, is exactly the same. The wonder has not been used up by the knowing. If anything, the knowing has deepened it. We are joined to all those watchers of the past, across all the centuries, by that single unbroken thread of looking up and feeling small and being, somehow, comforted by it rather than crushed. Because that is the strange gift of the vast, is it not, that feeling small beneath it does not have to hurt? We spend so much of our waking lives feeling that we must be large. We must matter. We must be seen. We must hold everything together. We must carry the weight of all our worries and our tasks and our tomorrows. And it is heavy, that trying to be large, heavier than we often let ourselves notice. But here, beneath the stars, beneath the thought of these enormous and ancient things, that weight can be set down. Here it is not only permitted but true to be small. The quark star does not need you to hold it up. The galaxies turned for billions of years before you came, and will turn for billions after you are gone, and they ask nothing of you, and they do not need your worry. And there is a deep and clean relief in that, in being, for a little while, gloriously and restfully small, one warm and breathing speck beneath a sky too large to measure, with nothing at all required of you but to be here and to breathe. Let yourself feel that now. Let yourself be small in the good way, the restful way. All the things you have been carrying, all the things you must do tomorrow, all the weights you have been holding up as though the world would fall if you let them go. Let them grow light for a while beneath the enormous quiet of the stars. The universe is very large and very old, and full of wonders you will never see, and it has been getting along in its fast and patient way for a very long time, and it will go on getting along, and none of it rests on your shoulders tonight. You are allowed to sit the weight down. You are allowed to be small and warm and safe and held beneath a sky that is doing perfectly well without your worry. And you are not separate from that sky, not truly. That is the other half of the comfort, and I want to hold both halves together for you, gently, because they belong together. You are small beneath the stars, yes, but you are also made of them. You are not a stranger looking in from outside at a universe that has nothing to do with you. You are a part of it, made of its oldest stuff, formed by its forces, kin to its wildest objects. One of the ways it has found here on this small warm world to look back at itself and wonder. When you look up at the stars, the universe is, in a real and not merely poetic sense, looking at itself through your eyes. You belong here. You are not an accident perched on the surface of an indifferent cosmos. You are the cosmos, gentled and cooled and gathered into a shape that can feel, resting for a little while in the dark, wondering about the crushed hearts of distant stars. To be small beneath the infinite, and to belong to it both at once, is not a contradiction. It is, I think, the truest thing that can be said about what you are. There is one idea from tonight that I would like to bring back now, softly, and hold up to the light one more time, because I think it has something quiet to say to you as you drift towards sleep. It is the idea of the ground state. Do you remember it? The deepest valley. The most restful place that matter can find. The state that everything would settle into if only it could find the road and rest there, needing nothing more. We spent a good part of the night wondering what that deepest resting place truly is. Is it iron, the contented nucleus at the bottom of the ordinary valley, the ash at the end of every star's fire? Or is it something stranger and deeper still, the strange matter of the boldest ideas, a valley lower yet, that ordinary matter can almost never reach, because the road there is blocked by a wall too high to climb? We do not know. But notice what the whole question is really about. It is about rest. It is about the state a thing settles into when all the pushing and the pulling and the burning are finally done, the lowest and quietest place it can find, where it can simply be without effort, without change, held gently by nothing but the way things are. All of matter, everywhere, is always seeking that rest in its slow and patient way. A star burns for billions of years, but only because it is on its way to rest. The burning is not the goal. The burning is the long road down toward the quiet remnant it will one day become. Every fire is a fire on its way to going out. Every star is a star on its way to its final stillness, whether that stillness is a slowly cooling white dwarf, or a neutron star drifting through the ages, or perhaps a quark star resting in the deepest valley matter can find. The whole universe, in a sense, is settling slowly across unimaginable spans of time toward greater and greater rest, toward the quiet valleys where things can finally lie still. And you, tonight, are doing the same thing. You are settling. All day you have been burning in your own small way, spending your energy holding yourself up against the pull of 100 cares, keeping the fire of your attention lit against the tasks and the worries of your waking hours. And now, in the dark, that fire is being allowed to bank down at last. You are letting the pushing stop. You are letting yourself sink toward your own ground state, your own deepest valley, the quiet place where you can simply be, held by the bed beneath you and the dark around you, needing nothing, doing nothing, seeking nothing but rest. You are, in your own soft way, doing what all matter does in the end. You are coming to stillness. And that is not a small thing, or a failure, or a giving up. It is the most natural thing in all the universe. It is what stars do. It is what the deepest matter does. It is what everything, everywhere, is always, patiently, on its way toward. To rest is to do the oldest thing that matter knows how to do. So let yourself do it now, fully, without guilt and without hurry. Let yourself sink toward the quiet valley. There is no wall in your way tonight. The road to rest is open, and it slopes gently downward, and all you have to do is stop holding yourself up and let yourself go softly down it. Your breathing is already slowing. Your body is already growing heavier, sinking a little deeper into the warmth beneath you with each slow breath. The weight of the day is lifting off you, thought by thought, care by care, the way heat leaves a cooling star, quietly into the dark, until there is nothing left but the gentle warmth of simply being here, alive and safe and settling towards sleep. And far away while you settle, the real stars are settling too. Somewhere out in the dark, right now, a neutron star is cooling, giving up the last of its birth heat across the long ages, sinking slowly toward its own deep rest. Somewhere, perhaps, a quark star turns quietly in the black, if such things exist at all, holding its impossible weight in perfect stillness, keeping its ancient secret, asking nothing of anyone. The whole sky is full of things coming slowly to rest, cooling, settling, sinking into their quiet valleys across spans of time so long they make the whole of human history seem like a single evening. You are one small warm part of that great settling, one gentle instance of the universe coming to rest, no different in your essence from the cooling stars, only softer and warmer and briefer, and awake enough for this one lovely moment to know that you are doing it. There is a phrase I keep returning to on nights like this. To rest beneath the infinite is to feel carried by it. I believe that is true, and I would like to leave it with you now to hold as you drift. You are not falling asleep alone in an empty and indifferent dark. You are resting within something vast and old and quietly magnificent, something you belong to, something you are made of, something that has been settling toward rest for billions of years and will go on long after you, and that holds you, tonight, as gently as the bed beneath your body, whether you feel it or not. You are carried. You have always been carried. The same forces that hold a star together are holding you together right now, and they do not tire and they do not rest so that you may. Them hold you. The vastness carry you. There is nothing you need to do, and nowhere you need to be, and no weight you need to hold. But this quiet and this breath and this slow and gentle sinking toward sleep beneath a sky full of wonders that ask nothing of you at all. I said we had left the workshop of measurement behind, And mostly we have. But there are a few more quiet marvels there that I did not want you to miss, and turning them over gently is itself a peaceful thing. The way you might, half asleep, keep turning a smooth idea in your mind for the simple pleasure of it. So let me share a few last ways that these hidden stars betray what is inside them, and then we will let the science go for good and drift the rest of the way down towards sleep. One of the loveliest clues comes from a small hiccup in the ticking of a pulsar. Remember that a pulsar is a spinning neutron star that sweeps a beam past us, so that we receive a steady tick-tick-tick as regular as the finest clock. Now a spinning star, left alone, should very slowly slow down, its ticks drifting ever so gradually further apart across the years as it gives up its energy to space. But now and then, in some pulsars, something odd happens. The star suddenly speeds up, just a little, in an instant, a tiny jump in its spin that we call a glitch. And then it slowly settles back toward its gradual slowing. What could make a whole star suddenly spin faster for a moment? The best answer we have is that the inside of a neutron star is not simply solid. Part of it behaves like a strange frictionless fluid, a superfluid, a liquid that once set spinning never slows, and this inner fluid can spin at a slightly different rate than the crust around it, storing up a little extra whirl until in a sudden moment that stored whirl is passed to the crust and the whole star gives a tiny leap. So from a small hiccup in a distant tick, we learn that these stars have strange fluid hearts, and how those hearts behave, and whether they are made of neutrons or perhaps of something stranger, presses once again on our long question. Even the smallest stumble in a star's rhythm carries word of what it is made of, if only we listen closely enough. Then there are the stars with the fiercest magnetism, the ones we call magnetars, neutron stars wrapped in magnetic fields so strong they are almost beyond describing, fields trillions of times stronger than the gentle one that turns a compass needle here on Earth, fields so powerful that they would, from a great distance, disrupt the very matter of your body. These stars sometimes give off sudden flares of high-energy light, brief and enormous outbursts as their titanic magnetic fields shift and snap and rearrange. And the way they flare, the way they ring afterward like a struck bell, can tell us something about the stiffness of the matter they are made of, about how the star quivers and settles after it is shaken. A star struck rings at a pitch that depends on what it is made of, the way a bell of iron rings differently than a bell of glass. And so even the ringing of a distant magnetar becomes one more faint voice in the long conversation about what lies at the heart of these objects. And here is a thought that I find especially beautiful, one of the strangest possibilities the mathematics allows. We have been speaking as though, for any given weight, there is only one kind of compact star that weight can make. So heavy a star is a neutron star, and only a neutron star. But some physicists have wondered whether that is truly so. What if, for a certain range of weights, two entirely different kinds of star could exist side by side, each with the very same mass but a different size? Ordinary neutron star of a given weight, larger and made of neutron matter, and next to it, so to speak, a quark star of exactly the same weight but smaller and denser, its heart dissolved into quarks. Two stars, twins in weight but not in nature, one gentle and one strange, both allowed by the laws, both perhaps real, scattered through the same galaxy. Physicists sometimes call these twin stars, and the idea that both could exist at once is sometimes called the idea of two families of compact stars, or of a third family beyond the white dwarfs and the neutron stars. It is only an idea, one more hypothesis among many, unproven and perhaps unprovable for now. But imagine it. Imagine two stars of identical weight, one of them ordinary neutron matter, and one of them a crushed sea of quarks, hanging in the same dark, indistinguishable by their weight alone, betrayed only by the small difference in their size, waiting for us to grow clever enough to tell them apart. If that is true, then the sky may hold a hidden population of quark stars, mingling unrecognized among the neutron stars, wearing the same weight like a disguise, waiting to be found. And that, in the end, is the shape of nearly everything we have said tonight. Waiting to be found. The whole subject sits poised, patient, at the edge of knowing. We have the tools now that our grandparents could not have dreamed of. We can hear stars collide. We can time the flicker of light around a spinning star's back. We can weigh a thing we cannot see and measure the ringing of a star struck by its own magnetism. And with all of that, we have drawn our net tighter and tighter around the quark star, narrowing where it could hide, ruling out this possibility and that one, closing in. But we have not caught it. It remains, tonight, a thing that might be there, hiding in the small differences, in the stars, too cold or too small or too strange, in the twins that wear each other's weight, waiting for the one clear measurement that has not yet come. And perhaps it will come in your lifetime. Perhaps someone will read these faint clues and see, at last, past all doubt, a star that can only be made of quarks. Or perhaps the door will quietly close, and we will learn that neutron matter holds the line all the way down, and the quark star will take its place among the beautiful ideas that nature, in the end, chose not to build. Either way, the not knowing tonight is a soft and open thing, a question left gently unanswered, and there is no need to hurry it toward its end. It has waited 50 years. Can wait through one more quiet night while you rest. Consider, too, before we turn away from the science for good, just how many of these strange stars there may be, hidden all around us in the dark. Our own galaxy, the great wheel of stars we call the Milky Way, is thought to hold somewhere between about 100 million and perhaps 1 billion neutron stars, scattered through it like seeds, cooled remnants of every great star that has lived and died across the long history of our galaxy. 100 million at the least. Perhaps 10 times that. An almost unthinkable number of these tiny, impossible weights turning quietly in the dark. And of all those countless neutron stars, how many have we actually found? Only a few thousand. A few thousand out of hundreds of millions. We have caught the faint ticking of a few thousand pulsars, the ones whose beams happen to sweep across the Earth, and glimpsed the glow of a few lonely others. But the overwhelming majority, very nearly all of them, we have never seen and never will, because they give off almost no light and their beams point elsewhere, and they are simply too small and too faint and too far to notice. They are out there, uncounted, unseen, a vast hidden population of crushed and cooling stars filling our galaxy, keeping their silence. And here is the thought that stays with me, the one I would leave you with as the science fades. If quark stars exist at all, then somewhere in that vast hidden multitude, mingling unrecognized among the neutron stars, there may be quark stars too, turning quietly in the dark, wearing the same weight like a disguise, indistinguishable at a glance from their more ordinary cousins. We may have already caught one long ago and given it a plain catalogue name and filed it away as just another neutron star, never knowing that we were looking at the densest matter in all creation. Answer to our whole question might be sitting even now in some old record, in some faint point of light we noticed years ago and thought nothing of, waiting patiently for us to grow clever enough to recognize it for what it truly is. Is that not a strange and lovely thought to carry into sleep? That the sky is so much fuller than it looks. Behind the few thousand stars we have named and studied, there lie hundreds of millions more we have never seen, and among them perhaps the very thing we spent this whole night wondering about, hiding in plain sight, keeping it secret, one quiet point of light among uncountable others. The universe does not hoard its wonders in a few rare and distant places. It scatters them everywhere, generously, uncountably, most of them unseen, most of them unnamed, waiting quietly in the dark, whether or not anyone ever finds them. And every one of those hundreds of millions of hidden stars was once, like our own sun, a bright and burning thing, and lived its long life, and died, and left behind this small crushed remnant to keep watch in the dark for ages upon ages. The sky is a vast and quiet graveyard of ancient suns, and also a vast and quiet nursery of the strangest matter there is, all at once, all around us, most of it hidden, all of it patient. That fullness settle over you now, softly, like a blanket of stars. You are not lying beneath an empty sky. You are lying beneath a sky teeming with hidden wonders, hundreds of millions of crushed and cooling stars turning quietly in the dark above you, and perhaps, among them, the answer to a question we have wondered about for 50 years. They are all up there, keeping their patient watch, whether or not you can see them, whether or not you ever know their names. And you may rest beneath them now, held by the quiet knowledge that the sky is far fuller and far stranger and far more wonderful than it looks, and that you are a small warm part of all of it, resting for a little while beneath its uncountable and patient lights. Let us think, gently and without any fear, about time on the largest scale of all, because there is a strange peace to be found in the very far future, in the slow and certain unfolding of things long after we are gone. The quark star, if it exists, is a creature of deep time, and to sit with deep time for a while is to feel the small worries of a single evening grow soft and quiet and far away. Our own sun, that steady, warm companion of every day of your life, is about halfway through its long and gentle life. For billions of years it has burned quietly, and for billions more it will go on. One day, far beyond the reach of any human concern, it too will run low on its fuel and swell into a great red giant and shed its outer layers softly into space and leave behind a small hot core, a white dwarf, the gentlest kind of stellar remnant, the first step down our staircase. The sun is not heavy enough to make a neutron star, let alone anything stranger. It will end its days as a slowly cooling white dwarf, glowing faint and dim, drifting on for ages, giving up its last warmth to the dark across spans of time so vast that the whole history of life on Earth is only a moment within them. There is no violence in the sun's future, only a long, slow, gentle fading, a quiet settling toward rest. The heavy stars, the great ones, they are the ones that make the strange remnants. And once made, a neutron star or a quark star endures. Does not burn, so it cannot burn out. It only cools slowly, giving up its birth heat to the dark over spans of time that stretch far beyond the present age of the whole universe. A neutron star born tonight in some distant galaxy will still be there, cooling, turning, long after the last ordinary stars have burned out and the sky has gone dark and quiet. These crushed remnants are among the longest-lived things the universe knows how to make, patient keepers of their strange matter, holding on through ages upon ages, outlasting almost everything. If you want a thing that endures, look not to the bright and burning stars which spend themselves quickly, but to the quiet, crushed remnants they leave behind, which keep their vigil in the dark almost without end. And in the deepest reaches of the far future, so distant that the numbers lose all meaning, some physicists wonder what will become even of these. Will the matter itself, given enough time, unimaginable time, slowly decay away into nothing? There are ideas, only ideas, that even the protons and neutrons that make up ordinary matter might, across spans of time so long they cannot be felt, very slowly come apart, so that in the deepest future even the most enduring remnants might quietly dissolve. And if the strange matter idea is true, then perhaps the quark stars would be the last to go, resting in their deepest valley, the most stable matter there is, holding on longest of all in a universe grown cold and dark and empty, the final quiet embers of a cosmos gone to sleep. I tell you this not to trouble you, for these are spans of time so vast that they can hold no fear, but because there is a strange comfort in the thought of it, that even at the very end of all things, in the deepest and coldest dark, there might still be these quiet stars resting, keeping their ancient secret, having settled at last into the deepest peace that matter can find. But that is all so very far away, further than any worry can reach, and we do not live there. We live here, now, in the bright and crowded morning of the universe, when the stars still shine and the sky is still full of light, and there is still so much to see. of all the times you might have been given to be alive, you were given one of the early ones, one of the times when the universe is still young and lit and full of wonders, when neutron stars are still being born and colliding and forging gold, when there are still people to wonder at them and instruments to catch their light. In the far future, the sky will be darker and emptier and quieter. But you are not there. You are here now in the light. And that too is a gift, a matter of timing, an accident of when you happen to open your eyes, and it happened to be early, while the show was still bright. There is no need to grieve the far cold future tonight. It is not your future. Your future is only tomorrow and the day after, a handful of warm and lighted days beneath a sky still full of stars, and that is enough, and it is more than enough, and it is, in its way, a kind of miracle that you should be here for it at all. So when the vastness of time threatens to make you feel small or fleeting, turn it around, the way you might turn a stone to catch the light on its other face. Yes, you are brief. Yes, the stars will outlast you by spans you cannot imagine. But you are here in the bright, early morning of it all, awake and warm and able to wonder, given a front row seat at a moment in the universe's life that will never come again and cannot be repeated. The quark stars, if they are out there, will keep their secret long after you are gone, but you are here now to wonder about them, and the wondering is yours, and no span of future time can take from you the fact that you were here, once, briefly, warm and alive and looking up. Let that be a comfort, not a grief. You have been given the light. You have been given the wonder. You have been given this quiet night. And now you may lay it all down, softly, and rest. I would like you to notice your own breathing now, if you have not already, without changing it, just noticing it, the slow rise and the slow fall, the quiet coming and going of the air. It is such a small and ordinary thing, and yet it ties you to everything we have spoken of tonight in a way that is worth resting on. The oxygen you are breathing was made inside a star. The iron in your blood that carries that oxygen through you was forged in a stellar death, in the very kind of fire that leaves neutron stars behind. Each breath you take is a small quiet transaction between the star stuff of your body and the star stuff of the air, an old, old chemistry, older than the earth, and it goes on without any effort from you at all, breath after breath, whether you are awake to notice it or lost in sleep. Your body knows how to do this. It has always known. You do not have to manage it or hold it up or keep it going by any act of will. It simply happens quietly, the way the stars simply turn, the way the cold remnants simply cool, the way the whole universe simply goes on being itself without needing to be told how. And there is a great rest in that, in the fact that so much happens without you having to do it. All day, in your waking hours, it can feel as though everything depends on your effort, as though you must hold your life together by main force, decision after decision, task after task. But the deepest things do not depend on your effort at all. Your heart beats without your asking. Your breath comes without your bidding. Iron carries the oxygen. The cells do their patient work. The whole quiet machinery of being alive hums along beneath your notice, tended by forces far older and far more reliable than your worry. And out beyond your body, the same is true on the grandest scale. The stars turn without your help. The remnants cool without your watching. The galaxies wheel through the dark, whether or not you spare them a thought. You are held on every side by processes that do not need you, and that is not a lonely thought, but a deeply restful one, for it means you may let go. Means the holding does not depend on you. Means you may sink into sleep and trust that everything essential will keep on happening quietly without you until the morning. Think of how much you have carried today. Think of all the small weights, the things done and the things left undone, the words said and the words held back, plans and the worries and the endless quiet effort of being a person in the world. You have carried all of it all day, and you have carried it well, and now, in the dark, you are allowed to set it down, to solve it, not to finish it, only to set it down, the way you would set down a heavy bag just inside the door at the end of a long journey, knowing it will still be there in the morning, but not needing to hold it now. Not tonight, not in this quiet hour that belongs only to rest. The quark star has waited 50 years for its answer and is in no hurry. Your worries, too, can wait until morning. They will keep. They always keep. And you will be stronger to meet them for having let them go tonight. Let your body grow heavy now. Feel the weight of it settling into whatever holds you, the mattress, the pillow, the warmth of the blankets, the gentle pull of the same gravity that shapes the stars, drawing you down softly into rest. There is no need to hold any part of yourself up. Let your shoulders soften. Let your hands lie open. Let the small muscles of your face grow still. The whole long effort of the day drains slowly away, from the top of your head down through your body and out, like heat leaving a cooling star quietly into the dark, until there is nothing left but the gentle warmth of simply being here, breathing, safe, and slowly, softly letting go. You are a small, warm part of something vast and old and quietly magnificent. You are made of the ash of ancient stars, arranged for a little while into a thing that can wonder and rest. You are held by forces that do not tire, carried by a universe that has been settling toward peace for billions of years, and holds you gently in its long unfolding. There is nothing you need to do. There is nowhere you need to be. There is nothing you need to solve or hold or carry, not tonight. There is only this quiet and this breath, and this slow and gentle sinking towards sleep beneath a sky full of wonders that ask nothing of you at all, and that will keep their patient watch through all the hours of the night, whether you are awake to see them or lost, at last, in the deep and healing dark of sleep. I want to tell you, before the night ends, a little about the people behind all of this, because the quark star is not only an object in the sky. It is also a long, quiet human story, a chain of curious minds handed one to the next across the years, And there is something restful in remembering that all this knowledge was gathered not by machines alone, but by people, ordinary people, who wondered. Think of the two physicists who, back in the year 1939, first sat down to ask how heavy a neutron star could be, before anyone had ever seen one, when the whole idea was fresh and daring and unproven. Robert Oppenheimer and George Volkoff, building on the earlier work of Richard Tolman, worked out with pencil and paper the greatest weight such a star could bear, and gave us the first version of that great limit at the edge of the cliff, the number we still refine today. They could not have imagined the instruments we would one day build. They had only their minds and their mathematics and their willingness to ask a question no one yet knew how to answer. And the number they reached for is still, all these years later, one of the central numbers of this whole story. Think of Arnold Bodmer, who in the early 1970s dared to wonder whether iron was truly the bottom of the valley, or whether some stranger matter might lie deeper still. And think of Edward Witten, who a little more than a decade later took up that same strange thought and developed it and gave it the force and the clarity that made the rest of physics take notice, so that the idea of strange matter, of a deeper resting place for all things, entered the conversation and has never left it. They were only asking a question, turning over a possibility, following the mathematics to see where it led. And it led here to a question we still cannot answer, a beautiful maybe that has kept careful minds occupied for half a century. Think of Rachid Ouyed, working in Canada in our own time, who imagined the violent conversion of a neutron star into a quark star and gave that imagined flash a name, the quark-nova, and wondered whether some of the brightest explosions in the distant sky might be its signature. Think of the countless others whose names we did not speak tonight, the ones who measured the pulsars and read the glow of lone stars and built the great instruments that listen for ripples in space, the ones who timed the flicker of light around a spinning star's back, the ones who searched old rocks for chips of strange matter that may not exist. Thousands of people, across generations, each adding a little to what the last had found, none of them living to see the whole story finished, each content to add their small stone to a cairn that others would go on building after they were gone. That is how nearly all deep knowledge is made. Not in a single flash of genius, but in a long, patient relay, a handing on of curiosity from one mind to the next across the years, each runner carrying the question a little further before passing it along. The quark star is not solved, and none of the people who first wondered about it lived to solve it, and the ones working on it now may not live to solve it either. And yet they work on it patiently, gladly, adding what they can, trusting that someone, someday, will carry it the rest of the way. There is a deep and quiet nobility in that, in devoting a life to a question you know you may never see answered, in being one small link in a long chain of wondering that stretches back before you and will stretch on after you. It is one of the gentlest and most hopeful things about our kind, that we are willing to do this, to plant trees whose shade we will never sit in, to ask questions whose answers we will never hear, simply because the asking is worth doing, and the knowing, whenever it comes, will belong to all of us. and you are part of that chain too tonight, in your own small way. By lying here and wondering about the quark star, by letting your mind reach out toward the crushed hearts of distant stars, you are doing the same thing those physicists did, the same thing the ancient watchers of the sky did, the same thing our kind has always done. You are wondering. You are letting the vastness in. You are adding your own small moment of attention to the long human story of looking up and asking what is out there. You do not need to solve anything, or measure anything, or prove anything. The wondering itself is the thing, and it is enough, and it joins you to everyone who has ever lain in the dark and let the stars fill them with quiet awe. That is a good company to keep as you drift towards sleep, the whole long line of them, all the wanderers stretching back into the deep past and on into the far future, and you among them tonight, one warm and curious mind, resting now, its wandering done for the day, sinking softly towards sleep. There is one more thing I would like to give you before we circle back to where we began, and it is perhaps the gentlest thought of all. It is the thought of how improbably, how impossibly, you came to be here at all, made of the very stuff we have spent this night wondering about. Follow the thread back with me slowly. The heavy atoms in your body were forged in stars that lived and died before the sun was born. Those stars, in dying, scattered their newly made elements out into great clouds of gas and dust, drifting through space. And from one such cloud, enriched with the ash of countless earlier stellar deaths, our own sun and its planets slowly gathered themselves together, about 4.5 billion years ago, the star stuff clumping and cooling and settling into worlds. On one of those worlds, the third from the sun, conditions were gentle enough for something extraordinary to begin. The atoms, those ancient atoms forged in stellar fire, arranged themselves into the first faint stirrings of life, and life once begun went on, changing and elaborating across billions of years, from the simplest specks in an ancient sea to the vast and tangled abundance of living things that fills the world today. And somewhere in that long, unbroken chain of living things, stretching back billions of years without a single break, without one link ever failing to pass life on to the next, is you. Every one of your ancestors, all the way back to the very beginning, survived long enough to pass life along. One of them failed. Through every danger, every hardship, every long age of the earth, the thread held unbroken, all the way down to you, lying here now, in the dark, made of atoms that are almost as old as the universe itself, arranged for this brief moment into a thing that can think and feel and wonder about the stars from which it came. When you consider the sheer improbability of it, the vast and delicate chain of chance and endurance that had to hold, unbroken, across billions of years, for you to exist at all, becomes almost too much to hold. So many things had to happen just so. So many stars had to live and die to make your atoms. So many ancestors had to survive to pass you life. So many turns of chance had to fall the way they did. And yet here you are, against odds too large to name, awake and warm and breathing, on an ordinary evening, wondering about quark stars in the dark. You are not an accident to be shrugged off. You are the improbable and precious end of an unimaginably long story, a story written in star stuff across billions of years, and the fact that you exist at all, that you are here to lie in the dark and wonder, is a quiet miracle that no crushed and distant star, however strange, can rival. And so, of all the matter in the universe, of all the ways it can be arranged, from the empty reaches of space to the crushed hearts of dying stars, to the naked quark seas we have wondered about tonight, you are one of the very rarest arrangements there is. You are matter that woke up. You are star stuff that learned, somehow, to know itself, to look back at the sky it came from and ask what it is made of. That is a rare and astonishing thing, and it is a comfort to me, and I hope it is a comfort to you, to think that you are not a small and meaningless speck, after all, but a rare and precious flowering of the universe into awareness, here for a little while, in the light, able to wonder. The quark star, for all its impossible weight, cannot do what you are doing right now, cannot wonder, cannot rest in the dark and feel grateful to be alive. Only you can do that, and things like you, and that is a gift that all the crushed matter in creation cannot match. So rest now, gently, in the knowledge of what you are. Not small, though you are small. Not fleeting, though you are brief. But rare and precious and improbable beyond all reckoning, a warm and wondering flame of awareness, kindled once briefly from ancient star stuff, given this one lovely night among all the nights of the universe, to lie here and breathe and be at peace. There is nothing more you need to be tonight. You have already done the most improbable thing there is. You have come to exist. And now you may simply rest in that and let it carry you, softly, all the rest of the way down into sleep. Let us walk the whole path once more, slowly, the way you might retrace a familiar road in your mind as you fall asleep, not to learn it again, but simply for the quiet pleasure of the walking. We began at the top of a staircase, in the gentle realm of ordinary matter, the matter of your hand and your pillow, matter so full of empty space that it is almost more nothing than something, held into shape by quiet forces you cannot see. That is where we live, you and I, on the softest and airiest step of all. Then we took a step down into the burned core of a dead star, the white dwarf, where a whole sun has been folded into the size of the earth, and a single spoonful weighs as much as a truck, held up by the stubbornness of electrons that refuse to share a room. And we took another step down into the neutron star, where a sun and a half has been folded into the size of a quiet town, only 12 miles across, and a single spoonful weighs as much as a mountain, held up by the stubbornness of neutrons that likewise refuse to be crowded past a certain point. Each step deeper, each step denser, each step stranger than the last. And then we came to the uncertain step, the one that may or may not be real, the quark star, where the neutrons themselves have been crushed until they dissolve, until the little prisons that hold the quarks inside each neutron melt away, and the quarks pour out into a single vast sea, matter crushed to the very last form it can take and still be matter at all. denser than a neutron star, smaller than a neutron star, a spoonful heavier than a whole range of mountains, perhaps held together not by its weight, but by the strong force itself, the same force that binds the quarks inside a single neutron in your own body, now stretched to hold an entire star. And perhaps, if the boldest ideas are right, made of the deepest and most restful matter there is, the true ground state, the lowest valley, the final resting place of all things. And below even that, one last step, the black hole where the staircase ends and matter falls away past every limit and even light cannot climb back out, and where our knowledge, honestly, ends too. The quark star sits just above that final step, right at the edge, in the last thin band of the knowable, one step short of the dark that swallows everything, including our understanding. That is where it lives, if it lives anywhere, at the very frontier of what can still be studied and reasoned about, and one day, perhaps, seen. Hold that whole staircase in your mind now, softly, all of it at once, from the gentle top where you rest to the crushed and cooling depths below. Feel how far it descends. Feel how strange it grows as it goes down, and how much stranger still at the bottom, and how much of it we do not yet understand. And feel, too, where you stand upon it, at the very top, on the gentlest step, made of the airiest and most spacious matter there is, the kind that can wonder, the kind that can rest. Of all the ways matter can be arranged in this universe, you have been given one of the rare and gentle ones, the kind that lies warm in the dark and thinks about the stars. The crushed matter at the bottom of the staircase cannot do what you are doing. It cannot wonder about you. But you can wonder about it, and you have all this night, and now the wondering is nearly done, and it is time to let the staircase fade, and let the strange stars sink back into the dark where they belong, and turn, at last, towards sleep. Somewhere out there, as you drift, the real stars are keeping their vigil. A neutron star is cooling slowly, giving up the last of its birth heat to the dark. Pulsar is sweeping its beam around and around, ticking out its patient rhythm to no one. And perhaps, just perhaps, a quark star turns quietly in the black, holding its impossible weight in perfect stillness, keeping the secret we could not quite pry loose tonight. They are all out there, cooling, turning, resting, whether or not we understand them, whether or not we are watching. And you are here, warm and safe and settling towards sleep, one small quiet part of the same great settling, one gentle instance of the universe coming to rest. Let them keep their watch. Let the question keep its patience. And let yourself now sink softly down toward the deep and healing dark, carried by the vastness, held by the quiet, at peace beneath a sky full of wonders. So let us return one last time to the question we set out with, all those quiet hours ago, and let us answer it as honestly and as gently as we can, now that we have walked the whole long road. What is a quark star really? And could a star exist that is denser than a neutron star and yet is not a black hole? Here is the honest answer, held softly in both hands. quark star, if it exists, is a star in which matter has been crushed one step further than a neutron star, crushed until the neutrons themselves dissolve and their quarks spill out into a single vast sea, no longer bound into separate particles but roaming free through the whole body of the star. Would be denser than a neutron star and smaller, holding more than the weight of the sun in a ball only 12 or 14 miles across, a spoonful of it heavier than a mountain range, perhaps held together not by its own weight, but by the strongest force in nature, bound quark to quark into a single quiet lump. And in its boldest form, the strange star, it might be made of the deepest and most restful matter there is, the true ground state of everything, more stable even than iron, the final valley into which all matter would fall, if only it could find the road. And could such a thing exist, denser than a neutron star, yet not a black hole? The answer, as far as we can tell tonight, is a soft and honest maybe. The laws of physics, as we understand them, seem to allow it. There is, perhaps, a narrow window of weight just below the final limit where a star must become a black hole, in which matter could be crushed past the neutron and still hold itself together, still be a star, still wear a face we might one day read. Whether nature actually builds anything in that narrow window, we do not yet know. We have candidates, stars a little too small or a little too cold, but none of them is proof. We have tightened our net around the possibility from every side, with pulsars weighed and glows measured and collisions heard, but the net is still empty. Quark star remains, after more than 50 years, a beautiful and permitted maybe, neither proven nor ruled out, resting quietly in the borderland between what our equations allow and what our instruments have caught. And I want you to feel, as you drift, that this maybe is not a failure. It is not a question we have failed to answer. It is a question the universe is still, gently, keeping open, a mystery held in reserve, a door left softly ajar so that there is still somewhere further to go. We live in a universe generous enough to be larger than our understanding, deep enough that no matter how far we reach there is always more, and the quark star is one of the quiet proofs of that generosity, one of the places where the universe is still deeper than our net can reach. There is nothing sad in a question left open. There is only wonder, and the promise of more wondering to come, handed on to whoever comes after us, the way it was handed to us by those who came before. So when you think of the quark star now, do not think of it as a puzzle you have failed to solve. Think of it as a quiet companion in the dark, a beautiful maybe turning slowly somewhere out there beyond all reach, keeping its secret gently, asking nothing of you, existing or not existing in perfect peace, indifferent to whether you understand it, content simply to be whatever it is out there in the vast and patient dark. It has waited 50 years for its answer, and is in no hurry at all. It can wait through this one quiet night, and the next, turning slowly, keeping its secret, while you rest, and wake, and rest again, and live your brief, warm life beneath a sky that will always, always hold more wonders than you can ever hope to know. And that is not a loss. That is the very thing that makes the sky worth looking up at. A sky with no more secrets would be a poorer sky. This one, full of quiet maybes, is the richer gift. There is something I keep turning over quietly as this night winds down, and it is the strange gentleness of that narrow window. Think about it with me for a moment, softly. For a quark star to exist at all, everything must be balanced just so. The star must be heavy enough that its neutrons are crushed past their limit, heavy enough to force the quarks out of their prisons. But it must not be so heavy that it tips over the final edge and falls all the way down into a black hole. It must sit delicately in a narrow band of weight, just past one threshold and just short of another, in a margin so slender that we are not even certain it exists. Too little weight, and it is only a neutron star. Too much, and it is a black hole. The quark star, if it lives anywhere, lives in the thin space between, in the balance, in the just enough and no more. And is that not a strange and lovely thing, that the most extreme matter that can still be a star should live in such a delicate balance? We tend to think of the extremes of the universe as brutal, as all or nothing, as crushing and absolute. And in a way, this is. But even here, at the very edge of what matter can endure, there is a narrow band of balance, a slender place where things can hold, poised between one fate and another, neither collapsing all the way nor springing back. Even at the frontier of the crushing dark, there is a margin where a thing can rest, exactly balanced, held between two extremes, being neither one nor the other, but something delicate and rare that lives only in the space between. I think there is a quiet lesson in that, if we want one, though you need not take any lesson at all tonight if you would rather simply rest. So much of what is precious lives in narrow bands, in delicate balances, in the space between extremes. Our own world is like that. The earth sits in a narrow band around the sun, not so close that it burns, not so far that it freezes, but in the slender ring where water can be liquid and life can hold. Your own body is like that, held in a narrow band of warmth and chemistry, neither too hot nor too cold, balanced delicately between states, alive only in the margin. The most precious things are so often the balanced things, the things poised between extremes, holding delicately in the narrow window where they can exist at all. And there is something tender in that, something that makes the precious things feel more precious, knowing how narrow the band is in which they hold. You are one of those balanced things. You are held right now in a delicate window of warmth and breath and quiet chemistry, poised between all the extremes that could unmake you, holding gently in the narrow band where a life can be lived. And it is holding. Tonight, as every night, the balance is keeping. Your breath comes and goes. Your warmth stays. The delicate window holds you, as it has held you every day of your life, without your having to do anything at all to keep it open. You are safe in the margin. You are held in the balance. And you may rest tonight in the quiet trust that the narrow window that holds you will keep holding softly through all the hours of the dark while you sleep and let you wake again into the light of morning. So let the thought of the quark star and its delicate window soften now into the thought of your own delicate window, the warm and narrow band in which you rest, and let both of them fade gently together into the dark. The star holds its balance far away in the cold and the silence, keeping its secret. You hold your balance here, in the warmth and the quiet, breathing slowly, growing heavy, letting go. Two delicate things, poised in their narrow windows, one crushed and distant and strange, one warm and near and precious, both holding, both keeping, both at rest beneath the same vast and patient sky. And now it is time, at last, to let the whole of it go, and to circle back softly to where we began, and to let this long and gentle night carry you the rest of the way home into sleep. Do you remember how we began all those quiet hours ago? We began beneath a clear and cool night sky, with the stars come out one by one, and you lying back, looking up, and somewhere in that darkness a thing we have never seen, giving off no light of its own, holding the weight of a star in the space of a town, wearing the face of something else entirely. That was where our journey started. And now, having wandered all the way down the staircase and back, having weighed the unweighable and measured the unmeasurable, and stood at the edge of the knowable, we come back softly to that same night sky, to that same quiet dark, to you lying back looking up. Nothing out there has changed. The quark star, if it is out there at all, is still turning slowly in the black, still keeping its secret, exactly as it was when we began. The stars are still scattered across the dark, just as they were. The night is still clear and cool and quiet. But something in you, perhaps, has softened over these hours. You have let a little of the vastness in. You have wondered about the crushed hearts of dying stars, and the deepest resting place of matter, and the strange delicate window where a quark star might hold. And now all of that wondering can settle, and quiet and fade, the way the stars themselves seem to soften and blur as your eyes grow heavy and the sleep comes on. The journey that began beneath the stars circles back now to where it started, to you, warm and safe, beneath the same vast sky, only sleepier now and more at peace. There is nothing left to think about. There is nothing left to solve. The question is still open, and it will keep, patiently, without you, until the morning and long after. You have done your wondering for the night, and done it well, and now you may lay it all down gently and rest. Let your breathing slow. Let it come and go, soft and unhurried, without any effort at all. Let your body grow heavy, sinking down into the warmth beneath you, held gently by the same quiet gravity that shapes the stars. Let your shoulders soften, and your hands lie open, and the small muscles of your face grow still. The last of the day's weight drains slowly away, from the top of your head down through your body and out into the dark, until there is nothing left but warmth and quiet and the slow, gentle rhythm of your breath. You are a small, warm part of something vast and old and quietly magnificent, and it is holding you now, as it always has, as gently as the dark itself. You are made of the ash of ancient stars, carried by forces that never tire, resting within a universe that has been settling toward peace for billions of years and holds you softly in its long unfolding. There is nothing you need to do. There is nowhere you need to be. There is nothing left to hold or carry or solve. There is only this quiet and this breath and this slow and gentle sinking down into sleep beneath a sky full of wonders that ask nothing of you at all, and that will keep their patient watch through all the hours of the night. Rest now. Let the stars keep their vigil. Let the strange and distant matter turn quietly in the dark, far away, keeping its secret. And let yourself go softly down into the deep and healing quiet of sleep, carried by the vastness, held by the night, at peace. Sleep well. Sleep gently. Good night.